We have one lecture to go, a double lecture to go, and then the research talk, and I think you're 100% right. The research talks do come at a different pace typically than the teaching lectures, so that will be evident for sure. So at the end of the last session, we were still, I challenged you to go work through a couple of tutorial questions. So I wanted to start just maybe flipping through what really happens with those drugs. On paper, you can write a lot of things out, but in reality, sometimes only some of them happen. So maybe we can click through a couple of those examples here. Linazolid was the first one that we looked at, and several structures are present in the drug. The predominant metabolism occurs on this morpholine ring system here, so you can get O dealkylation. If you get O dealkylation, you can get to metabolites like this that simultaneously occurs with N dealkylation, which would be the process right there. So the initial O dealkylation would make something that looks like this, and then the N dealkylation would cleave this carbon-nitrogen bond, and that is a process that occurs to a reasonable extent. Additionally, you see a lactone, or this type of a substructure here. You have an alcohol and an ester, and that can make an alcohol and a carboxylic acid, that can make an ester. Not something we predicted, but chemically it makes sense when you just think about basic reactivities of those functional groups. The other key metabolite derives from N-dealkylation. You get a substructure looking like this, and that undergoes clearance. So hopefully the types of things that you would draw in this case, the fluorine atom does modulate the metabolism a little bit here. Maybe a key point to note, a second reason why we don't see as much metabolism here, is that in general, drug metabolism typically occurs on the periphery of molecules. It usually doesn't happen to the middle of the molecule. You know, think about a molecule approaching that heme, and that heme is kind of in a cavity that's kind of like a cone. It's conical. And so the appendage of your molecule needs to be able to stick into that cave, basically. And so many times it's difficult for the middle part of a molecule to fit down into towards the heme in the P450. So more commonly, you're looking at the periphery of the molecule as the sites of predominant metabolism. Now, the second one, dasatinib, is a kinase inhibitor, BCR-ABL kinase inhibitor for leukemia. And this has all kinds of substructures all over it. And you could predict a lot of things, and in reality, a lot of things do happen. So there's all kinds of stuff occurring to this molecule. Maybe we just start over here. We get benzylic hydroxylation. Hopefully some people saw that. The electron-rich aniline can also undergo aromatic oxidation. Okay, now this specific metabolite has two resonance donating groups in addition to an inductive donating group. So it actually undergoes further redox chemistry. It can further oxidize, and that's when you get to this quinone, iminoquinone type substructure. And so this can actually be hepatotoxic. It can be bad for the liver because this can react with other proteins. Now, when we look at the rest of the molecule, there is not that much metabolism going on through the core of the molecule, as I mentioned before, and it's usually the peripheries, the appendages, the things that can stick down into towards the heme. Those are the sites of predominant metabolism. So you see some oxidation of the alcohol by CYP3A4. That's just abstraction of the CH bond. It makes an aldehyde, and then you do it a second time and it makes a carboxylic acid. N-dealkylation can occur. You get a metabolite like this. You can also get some N-oxidation. There's a nucleophilic lone pair of electrons. Certain P450s will do that transformation too. Not one of the main ones we covered, but it still happens. Okay. So hopefully these are some of the metabolites you might have drawn on your own for homework. Maybe we can look at sertraline. This is a neurotherapeutic, and the structure is shown there. This has a couple of metabolic processes that occur. The amine itself can undergo dealkylation at two different positions. There are two different alkyl groups coming off of that amine. The demethylation process can occur, and you get to this primary amine. But you could also, if you look over here, That's an aliphatic system over there. So you can get N-dealkylation the other way also in this case. And that's a benzylic position. That benzylic position is always also activated. So if you do N-dealkylation over here on this side, you get to the ketone, the decalone system. Okay, so that's how we're getting there. You can also, again, do the first dealkylation, then do the second dealkylation, get to the same metabolite. This has been rigorously established. You can see which P450s are responsible. Sometimes it's like one or two, sometimes like everything does it, and this is the case where everything does it. Phase 2 can also happen, and we predominantly talked about alcohols and the examples we looked at, but amines are also nucleophilic and can undergo phase 2 processes or conjugative processes. And so here's a series of glucuronide transferases that'll transfer they'll transfer glucuronic acid over to your substrate. In this case, it's going to be tethered to through a carbamate. So, how are we doing? Some people draw out those, I hope. Okay. We already talked about this example, the final example that I had there. I actually forgot to present and give you guys a question, but I think you have most of the slides for this. You can see where the sites of metabolism are, the big greasy T-butyl system. There's a lot of grease over on this portion of the molecule. You can also get some O dealkylation here, and that can actually undergo further redox chemistry, but I'm not talking about that right now, okay? So again, hopefully people would look at this type of molecule and predict those two metabolites. This ring is electron rich. If you see aromatic hydroxylation, maybe you would expect that to occur over here. This one is more deficient. Those nitrogen atoms pull electron density away from the pi system. And so you would anticipate, just based on electronic structure, that this one would be more deactivated relative to this one. Okay. For aromatic hydroxylation purposes, also, for aromatic hydroxylation purposes, we might look at this ring. The T-butyl group is slightly donating, but the sulfonamide, this is a strong electron withdrawing group, that SO2. And so you are electronically deactivating this ring system over here. Now there's no fluorine on this drug, and that's fine. There are derivatives for which you can use fluorinated substituents to decrease the metabolism. So here's some representative T-butyl replacements that one might explore. And so again, that's in the slide. So I'm going to pause, see if there are any questions about those examples. Are we good moving forward and jumping into the next formal lecture? Let's do it. Okay. So let me close that slide deck. We are now on November 7th. Is that right? All right, November 7th. So it's tricky because back in the US, they're going to sleep. So I had to call home this morning and say, God, what day, what time is it over there? When I'm saying good night to family. But here we go. This is a fun one, ligand-protein interactions. This is a fun lecture. It's very physical in nature, and hopefully everybody learned something from this one. And you have to write it down on your reports too on the PDF. You know, talk about how much you learned. You can use this slide deck as a source. So, drug design, drug discovery, zeroth law. I've covered this a couple of times. In order for a drug to exert pharmacological action, it needs to get to the site, it needs to persist in the site, it needs to circulate throughout the body for a sufficient amount of time that it exerts pharmacological action prior to clearance. Okay. So we covered a lot about that circulation, the distribution, the clearance, but now we have to ask the question, well, what if that drug actually does get to the site, the intended site? And what if it does engage the receptor? And how might fluorine perturb the interactions at that receptor? So now we start asking that question, and we start thinking about intermolecular interactions. And so I've summarized those here. This is a 2-slide summary. We're going to walk through the different types of interactions that are common for fluorinated substructures. These are kind of summary figures, but we'll talk through these in more depth as we go through. And then in a second part of the talk, probably after the tea break, we're still taking a tea break? Okay. At what time officially? 11:15 or okay. In a second series of examples, we're going to talk about how fluorination can change the acidity and basicity and really perturb other binding interactions. We talked about basic amines. We're going to talk about some other ones also, and how you can have unique functional groups for which fluorine really drives the reactivity of that group. Okay. So let's just first start with the multipolar interactions. This is a classical interaction now. It was recognized just over 20 years ago by Francois Diederik. And so this is an electrostatic interaction. It's an interaction for which the CF bond's dipole presents the anionic portion towards an electrophilic carbonyl. So it's electrostatic in nature. It's not a hydrogen bonding interaction. It's roughly perpendicular to the carbonyl. You can see representative examples of the CF bonds. These are models that come out of the crystallographic database, the structural database. And we're just looking at the pink ones. The green ones are something else. The pink ones are your multipolar interactions. And all of these interactions, the fluorine is pointing mostly towards the carbonyl carbon. And there's a certain distance and certain angle associated with this type of interaction. So that's what this chart is for. It's looking at the angle of the interaction. 90 degrees, that's perpendicular. Here's our carbonyl, here's our CF bond. It's like that. The chart, you can see the curvature here. You can see the curvature, okay? The chart indicates that when you're close to 90, when you're close in distance between the fluorine and the carbonyl carbon, that thing is perpendicular. Within 10 degrees, that thing is like that. As the distance increases, the angle can change a bit. Okay? And that's what you're seeing out in this region over here. As you get out past 3 angstroms, towards 3.5 and maybe 4 angstroms, you see more variability in the angle, but the CF is generally presented towards that carbonyl carbon. And again, it's electrostatic in nature. The rough distances associated with this interaction are here if you're looking at crystal structures or computational modeling using whatever computational package you prefer. That's what you're looking for. The CF presented towards the carbonyl at roughly these distances and roughly this angle. The energy associated with this interaction is about 0.5 kcal per mole. A little more, a little less. There's a little bit of error there. But it's a reasonably weak interaction, but it can be pretty profound in drug discovery campaigns. So in a follow-up manuscript publication, a series of matched pairs were analyzed, and in this case you'll have like H versus F, CF3 versus methyl, CF2 versus CH2. So that's what we're looking at in matched pairs. These types of substructures, and we're going to compare the affinity of the drug for the target as a function of H versus F. And in this analysis, you get an increase in potency at the target 50% of the time. Okay? If you can observe this interaction in your crystal structure or your docking model, you have a 50% chance of having a more potent compound when you put fluorine in there. So it's a coin toss, 50-50. Okay? Sometimes you have no change, sometimes you get a decrease. So why not try? About a 50% chance of a lot of things in life, that's actually a pretty good chance, right? So the suggestion here is, or it's an explanation of, yeah, sometimes you put it in there and it's making a nice interaction. Sometimes it's not really doing much. Sometimes it gets a little worse. Why not try? But recognize that it does get worse sometimes. It can be no change sometimes. If you look into this data set here, the distances where you get an improvement in potency are typically outside of 3 angstroms. Okay? There aren't many examples for which the fluorine to carbonyl distance is less than 3 angstroms. So if you start getting too close, it's not likely going to be in this bin where you get an increase in potency. Okay? So it's something to think about. I know we kind of, on the previous slide in the previous study, gave you a range here. That was from this 2003 paper. This one's a little bit newer, a different analysis, and it's suggesting you should actually be looking outside of 3 angstroms, not that 2.8 in that range. Just don't worry about that, is what this one's suggesting. Okay. Do what you want in your own programs, but that's just a suggestion. Now remember, fluorination If you fluorinate molecules, we already saw in several other lectures that you can improve other properties. So if you get no change in potency, but you've improved other properties, that can still benefit your program. Similarly, maybe there is a slight decrease in potency, but other molecular properties, other metabolic properties, other distribution properties improve. That might still be the right way to go for your personal campaign, for your drug discovery campaign. So don't take this out of context. Don't say this is always bad. Sometimes you get benefits in other properties even if your potency goes down. So keep that in mind as you move throughout your career. So the discovery of this interaction, again, I mentioned it's over 20 years old now. It came from an analysis of a series of ligands for which fluorination was systematically studied around a benzylic ring coming off of the substructure shown here. The pocket had several residues. It was a well-defined pocket, and it provided an opportunity to say, what's going on if I fluorinate each position? And in this specific case, there was one position, the 4-fluoro position, for which the potency increased pretty drastically, and the selectivity versus other enzymes also increased. So look at that change in potency relative to other examples in the class. We're going to come back to this later on, like pretty late in the lecture, and look at what goes wrong when you have bad binding interactions. But right now we're just asking the question of what's going to be good. And the analysis that was conducted with a specific enzyme identified the multipolar interaction that I was just mentioning. So the fluoro at the 4 position is presented towards the carbonyl carbons. Okay, that's this one right here, 3.5 angstroms, and the rest of the environment was also analyzed. And when you do that analysis, you can then go back into the crystallographic database and see how many other types of co-crystal structures have this type of substructure. And it turns out that quite a few do. The multipolar interaction that I was indicating is here, but there also seemed to be quite a few structures for which there was some type of favorable interaction with the C-alpha. Dr. Deepak on day 1 was talking about the acidification of the CH and how there's many interactions between a CF bond and a CH bond. And it turns out that many times this multipolar interaction, since it's close in distance, this carbonyl is close in distance to the vicinal CH bond, by default, you also see an interaction there, okay? So that's what's going on here. This is what's called a fluorophilic environment. It's been analyzed by many individuals. You're really looking at the carbonyl fluorine interaction, but also an interaction sometimes with the alpha CH. And that makes sense, right? If we're pulling the carbonyl, if we're pulling the CF bond towards the carbonyl, and the next carbon over is going to be pretty close also. And I think that's what's going on in this case. So there's some more data for you to walk through and look at. I provided on the slide. The paper is fantastic, like it's really rigorous science. It's a great one to dig through, and it's a fluorine classic. One key note is that when you look at these plots, there are gaps. So there are some areas that you should stay away from. You can see a gap down here below 2.4 angstroms for DT. You can see a gap over here. Now this axis here is D1 versus D3. So it's D1 versus the carbon distance right next to it. And so basically what it's suggesting is that if you have a short distance for D1, you can't be far on D3, right? If this distance is close, that one can't be far away. Kind of makes sense when you just think about geometry, right? The second one is also interesting. If we look over at this chart, below 2.4 on D2 doesn't really happen. So you cannot get this distance too close. Okay? So that's a second point to think about and just consider, and there's a lot of data points, but those I think are the two main messages. And it's not a bad chart to look at if you ever try to use this type of strategy or analyzing a crystal structure. You can always open up the paper if you know these charts are here and go back and look at the data in real time as opposed to trying to memorize these things. These are things I wouldn't memorize normally. Okay? So there are some regions that you want to avoid if you're trying to rationally utilize this strategy to drive potency. Okay. So these interactions, I said, had been found in a wide variety of crystal structures. So we pulled a couple of of them from my group. This is probably from 2017, 2016, when we were building up the initial slide decks. And so I'll just show you a couple that we pulled out of the literature. Here's an example where you have a couple of interactions, 3.5 angstroms over to one carbonyl, but you also have another one. The next position over also presents a carbonyl at just under 4 angstroms there. You can see an increase in potency from these types of interactions when you assess the data for the match pair. Okay. Similarly, another example. This is another match pair for which we get an improvement in potency, 6-fold improvement by placement of a fluorine atom here, 3.2 angstroms for the fluorine atom to either of the carbonyls. And another evaluation, another estimate, you can see it right there. Now in this case, the alpha carbon there has a distance where you think, okay, maybe that secondary interaction is also present. In this one over here, you can see the alanine methyl is actually presented towards. So this CH bond is going to be presented off the page. So that one does not have the CH bond associated with the interaction. Okay, so the CH bond is kind of optional. Sometimes it's there, sometimes it's not. But in many cases, enough cases, statistically it is present and it can be favorable. Okay. So those are the multipolar interactions. They're also really important for at least one really important approved therapeutic. This is the development of Lipitor. This is the #1 selling drug of all time for well over a decade. It was making $11 billion a year for Pfizer, for about a decade, some maybe about 15 years ago. So in the initial discovery, this was the pharmacophore. So this is a pharmacophore. It actually saponifies. You get an open chain substructure, and that replicates a metabolite, HMG-CoA, that the body uses to make other steroids. So initially they were studying this series. You can see a heterocycle. When you go back and look at the older literature, they had a variety of different heterocycles that they were exploring. In many cases, they were doing SAR, evaluating SAR on an aryl ring here, the 2 position relative to the aliphatic system here. So the fluorine atom at this position drove affinity pretty significantly, potency pretty significantly relative to H. And other polar substituents, hydrogen bonding substituent here with the hydroxyl also improved affinity. You can see methoxy was a little bit worse, chloro was okay. And that study, after further analysis, decades later, right, this is 1990 and this is 2001, they realized what's really going on here, and you have a multipolar interaction. I introduced that multipolar interaction initially for a carbonyl. But other C something double bonds, in this case a CN double bond, also has electrophilic character, delta plus character at that position. And you can see the distance, 2.9 angstroms. You can see the improved potency of the ligands and match pairs at this position. So ultimately we have another multipolar interaction that was present for well over a decade, but nobody really realized what was really going on with these systems. Okay? So that's what's going on there. It's one fun story. You can see how the rest of the drug ultimately developed, a little bit more grease over here, coming out of this position when you get to the methyl group. And then you can further build greasy substituents off of these positions over here. And yeah. Cool? Okay. Yeah.
You have written there no interaction with NH with NCF. But it is probably the polar interaction will be with carbonyl basis.
Yeah. Yeah. So that's what a multipolar interaction is, and nature chose to do this. Nature chose to say that there's delta plus character there, and there's an electrostatic interaction. Now, intermolecular hydrogen bonding interactions is like the very next section. I'm looking at the next slide, and so that's like the next section, and we're going to talk about what else can happen, but also recognize that the geometries to have some type of an interaction with the NHs there would be different. You'd have to have some type of a rotation of the side chain of the amino acid to be able to get proper alignment. So we can cover that in like 2 slides.
And also you have, previously you have told there is intramolecular hydrogen bonding probability is more than in case of fluorinated compound. So,
Absolutely. Intermolecular hydrogen bonding is controversial. Some people say it doesn't exist. But there's a different explanation. And like we're 1 slide away from it. So may I move forward and then let's get to the end of the next section, and then we can pause and come back and come back to this question or discussion. So that summarizes the multipolar interactions, at least for an initial introduction. There's so many examples out there in the literature. There is other literature that follows up on the papers I've presented here. We can now move and talk about the polar interactions. So when we talk about polar interactions, these are the interactions that some people think are hydrogen bonds. Okay, now hydrogen bonding interactions require the lone pair of electrons kind of reaching out to a proton, and there's some type of an overlap, but fluorine holds its electrons really close. In many cases, the interactions, when you look at the crystal structures and the distances, like they're not within distance for those lone pairs to actually be reaching out and grabbing the proton. So there's another interaction that can also explain that same feature, and it's dipoles. You think about magnets, plus charge, minus charge, plus charge, minus charge. You might have a good alignment of the dipoles that's still favorable. It's not the overlap of the lone pair of electrons reaching out to a proton, but alignment of the dipoles can still be felt through space and at longer distances. And that's the other explanation in this controversial argument about intermolecular hydrogen bonds. Okay? So I can walk through that a little bit more. Sorry, I left my tool over there. So we can talk about that a little bit more on this slide. Okay? Hydrogen, or these, what we'll call polar interactions, are typically weak. Less than a couple of kcal per mole. You get a good hydrogen bond, like 5 kcal, 10 kcal per mole. You can get higher, but you easily get 5 or 10 kcal per mole. These are like minor, less than 2, sometimes less than 1. In terms of the dipoles that I was just talking about, think about the electronegativity of a CF bond, right? Anionic at fluorine and a acidified proton that would typically engage in a hydrogen bonding interaction. That's going to be delta plus, and this is going to be a heteroatom, delta minus, and it's going to be an electrostatic interaction, alignment of those dipoles that's driving the affinity. Okay? So that's the alternate explanation. I've seen heads nod. We're kind of okay enough with the background on this type of an interaction. They are a little bit weaker than a good hydrogen bond. They can be used to tune molecules pretty well, late stage selectivity. You can get some affinity, but it's not always that great. So here's an example. This is Januvia. This was one of the examples when we were looking at oral bioavailability, and I said, you guys go calculate the pKa. Somebody did it. We walked through the math, and it was like a 5-fold difference in pKa between these heterocycles over here. So we've seen the drug structure, and now we can start thinking about not the pK properties, but we're going to start looking at the affinity properties and what happens when you walk through systematically substituents on the ring and on this position here. How does that affect potency against the anticipated target? In general, these are very selective ligands. These are other anti-targets that they're trying to avoid, and you don't have much interaction with any of those. So I'm not going to discuss the right hand, but that was just included to show we have good selectivity for the scaffold. So in the initial subset of molecules presented here, you can see the R2 group is increasing in terms of grease, steric bulk. You're going to see an increase in potency as you just put greasy substituents into that space. The CF3 is definitely more potent. But you don't necessarily have a huge jump. That's like 3-fold, 3.5-fold. That's not amazing for getting 3 fluorine atoms well positioned with good intermolecular interactions. Those are pretty minor improvements in potency there. In contrast, arrangement of the fluorine atoms, the monofluorine atoms around this ring, seems to drive affinity much more significantly. And so in this series, we go from a 3,4 difluoro to a 2,5 difluoro. 4 is para, 3 is meta. So you're kind of going from this to a 2,5. Okay, there's a lot of examples in this MedChem paper. I've just selected a couple. And you see an increase in potency. That's a big jump. That's a 5-fold increase by just repositioning the fluorine atoms around the ring. It's just isomers of each other. So if you get your fluorine atoms properly aligned there, you can really drive affinity. You put a fluorine back in the 4 position, you drive potency a little bit more. This is one reason why many in the pharmaceutical industry, like, don't try to outthink nature. It might be easier just to build the subset of derivatives where you just like make as many perturbations as you can and just test them all and see what works and then come back and rationalize it as you're building your model and getting data to revise your model. Okay, maybe if we're thinking too much, maybe we might miss one that would be good, and so you don't want to. So many times people will just try to make as many derivatives as possible when they're trying to tinker around with fluorine. So, anyway, we have our CF3 still here. If we take this 2,4,5 trifluoro and revert back over there, you see that we do retain some affinity, like we're still 2-digit nanomolar here. Remember, this substitution also drives the oral bioavailability pretty significantly. So you do want that CF3 there for other purposes. Okay. Finally, further tuning of the ligand says if you get too big, too bulky in that space, again, you lose potency again. So tuning, how big and bulky the substituent is was pretty significant, and there was high selectivity there. Subsequently, the models demonstrated that in this case, you're dealing with the polar interactions, and the CFs seem to make interactions that aligned with the polar amino acids. These are ones that did not align with multipolar interactions. They seem to have better alignment with the fluorine kind of engaging the hydrogens in those substructures. You can't always predict it, right? The enzyme has some amino acids that are a little bit floppy. Sometimes it's a little bit more rigid of a receptor. And sometimes you might be predicting one, but the receptor reorganizes, and then you end up with an NH with an arginine instead of that multipolar interaction with an arginine. So, sometimes you get one, sometimes you get the other. Okay, and there seemed to be some type of an interaction over here in this pocket with polar residues similarly. Okay, so these types of interactions do exist, and in other follow-up drug campaigns for the same target, individuals try to retain some of these interactions. So you can see other scaffolds that other companies have used to probe and or develop clinical candidates in this chemical space. This fluorine atom is retained even if you change a lot of the rest of the scaffold. Okay, so those are cool scaffolds, though, the way they've kind of jumped and really different chemical structures there. But that interaction is still really important. Okay. So, the couple of interactions that we have talked about already are unique to fluorine, and many individuals will mistakenly call it a halogen bond or halogen bonding interaction, and that is absolutely 100% not true. It's chemically the opposite, and I'll explain why on this slide. So I'm trying to dispel a myth that any of these interactions, the first one we talked about, the multipolar or the polar-polar dipole alignment, those are not halogen bonds. So halogen bonds are bonds in which there's a sigma hole. There's delta plus character over in this space that's part of the Ci sigma star. I'm going to have another representation. We'll keep building the slide in a little bit. And you have a pi system, or nucleophilic lone pair of electrons present its electrons into the sigma hole. And so the orbital overlap diagram for this type of interaction is shown here. Again, the sigma hole is predominantly composed of the CX sigma star. That sigma star is kind of in this space. There's delta plus character there. The sigma hole accepts electrons from pi systems and or lone pair of electrons. Okay? And so the orbital mixing diagram puts 2 electrons down, no electrons go up, and it's a net stabilizing interaction. These can be up to 20 kcal per mole. They can be pretty powerful and really well-designed systems. The energy levels or reactivities of the sigma holes, the sigma star, increase as a function of the size of the halogen. So Ci bonds have bigger sigma holes than CBr, bigger than CF, and then, CCl, and then CF does not have a sigma hole. The CF bond does not have a sigma hole. You cannot project nucleophilic lone pair of electrons into a fluorine atom. That's bad. That's going to be electrostatic repulsion there. Okay. And you can see representative examples of the sigma hole in these examples here. CF4, there's no sigma hole there. Cl, there's a little bit of cationic character. Bromine, iodine, you see more and more and more cationic character in this space that can accept electrons. This type of a charge transfer complex are also called charge transfer complexes. Okay. So that is a halogen bond. The only way fluorine can participate in a halogen bond is if it's actually this over here, donating its electrons into the sigma hole. But still, fluorine holds its electrons close to itself, high electronegativity. It doesn't like to send its electrons out into this space. So these aren't, fluorine here, it's not a predominant interaction. It's nowhere near as common as having maybe an oxygen or a nitrogen. Okay. Now, fluorine can participate in a related interaction in systems, and so these are related charge transfer complexes by which you can present electrons from either a pi system or nucleophilic lone pair of electrons. You can present those into a sigma hole on a carbon-sulfur bond. So the orbital mixing diagram would look very similar. You have a sigma star from the CS bond. When it overlaps and you get this interaction with either the pi system or the lone pair of electrons, the electrons donate into the new mixed molecular orbital, this bonding orbital, but the anti-bonding orbital is vacant. So you get a net stabilization, and these can be reasonably powerful interactions. And you can see that the sigma holes that have been calculated, those sigma holes are anti to the carbon-sulfur bonds. This is a thiophene, but there's also sulfur in some proteins, many proteins. We have our methionines, we have our cysteines. So if you have, for example, a methionine, the active site or the site you're trying to ligate with a small molecule or a large molecule, the site you're trying to target, you might be able to engage the sigma hole with some type of nucleophilic residue in your drug. And yes, fluorine can participate as a donor in these types of interactions amongst other atoms, but fluorine can do it too. And this is a fluorine class. We're going to talk about the examples of how fluorine can work here. So in this series of molecules, you have a carbazole, you have the ethyl chain attached to it. The initial monofluorinated derivative presents into this is supposed to be going 3.4 angstroms through the CH there, 3.4 angstroms over here. And what we have is some type of an interaction that would look something like this. This is supposed to be going down into this space. We have an interaction that looks something like this. You have those multipolar interactions. It's just well aligned. You have conformational freedom in this ethyl chain for that fluorine atom and the ethyl chain to kind of find the happy spot over there. The CF2 unit still makes the same interactions over here, but it also starts to make an interaction over to the sulfur, and the CF3 actually reinforces that interaction. So in the CF3 version, you still retain the initial multipolar interactions we saw before, and now you see the really nice alignment here with the sigma hole, 180 degrees roughly, so it's presenting anti to the carbon-sulfur bond. The distance you can see there, 3.2 angstroms, looks like a bonding interaction. And you can see the improvement of potency from 138 micromolar, which It's not bad. This is a fragment-sized molecule. It's not a real drug yet. They need to build quite a bit more. It's a nice model system for understanding what's going on with the fluorinated substituents, but we can get down to a sub 40 micromolar compound with these substitutions. So, okay. So we can engage proteins through these interactions, through fluorine-sulfur interactions, but you do need to be aware of the distances and angles there and try to optimize those if you're going to have a success with these types of substructures. Okay. So those were several different examples of polar interactions that can occur. Let's talk about hydrophobic interactions. So what's the nature of a hydrophobic interaction? Maybe that's the first thing we should talk about. Generally, we think about drug design and interactions between a ligand and a target. We're trying to think of affinity interactions, hydrogen bonds, pi-pi interactions, side-phase pi interactions, multipolar interactions, just sort of favorable interactions. And those can certainly drive affinity by changing delta H. If we have an energy associated with binding, delta G equals delta H minus T delta S. We've known that since high school chemistry, right? Okay. So the molecular interactions that we've been talking about before really affect the enthalpy term, but you can also drive affinity by modulating the entropy term. And when we talk about hydrophobic interactions in a general sense, one way that these enthalpic interactions occur is actually by displacement of water. So you might have organized water networks within a hydrophobic cavity, hydrogen bonding with each other, water in that space. If and when the ligand displaces the water, that water is pushed out of the active site into bulk solvent, that is entropically favorable. That'll affect the delta S term, and that can also drive affinity. The greasy molecule doesn't like being in an aqueous environment, so it wants to push itself into a hydrophobic cavity. And when it does that, the displacement of water drives the delta S term. Okay? So when you have finely tuned, well-tuned grease of the right shape, right size, you can really drive potency. Now, when you add grease, you have to be aware that that grease could get metabolized, and then we've got to be concerned about other PK properties. So there's a balance, and that's why I was telling you about the lip-E, lip-met-E, those types of metrics. Those metrics evaluate, number one, when you put grease on the molecule, are you really gaining affinity? That was one of the types of metrics we were looking at. And in the other metric, we were saying, okay, if we add grease, how much is metabolism increasing? And you have to balance those. It's not like you can win all the time in both of them. Like you might make a change and one might go up, the other might go down, and you're going to be fine-tuning and balancing these types of properties. Nonetheless, the key point here is that we can also modulate affinity for a target through pushing water out of the active site. Now, this comes with several caveats, and so the generalization is not always true in specific examples. So in specific examples, you might have really well-organized water networks, and if you push a greasy moiety through a really nicely aligned water network, that might actually be bad for enthalpic purposes. So the general trend is shown here. Well-positioned grease can displace water and improve the entropy of the system, but sometimes that's not always favored in every single example. And many times the modeling systems most modeling systems don't explicitly track water that's bound right around the ligand there. Sometimes you have to actively model that in, and when you have like more extensive networks, that's even tougher. But there are some really nice examples out there of these hydrophobic interactions and what these hydrophobic pockets might look like. So here's one example. This is that cannabinoid compound, one of the ones we studied when we were looking at the PK. Remember, we started with a neutral phenolic ether here, and then we added electron withdrawing groups. Metabolism switched over here, and then they had to solve metabolism over there. That was that example. Okay. So in this system, the CF3 group actually improved potency. The data is back in your previous slides, but you also, it drives potency because you're presenting this moiety into a greasy pocket and pushing water out of that space. Okay, that's what's going on in this system. There are other systems that we're going to look at that allow you to really think a little bit more critically about the data and what's going on with water and reorganization of water. So this is a match pair analysis of a cyclic nucleoside. So you can see that the nuclear base on both sides, and then you can see the cyclic nature right there. Okay. Crystal structures for these can be obtained from the crystallographic database. In the crystallographic database, the compound with a hydroxyl group has a nice hydrogen bonding interaction with water. 2.4 angstroms, the fluorinated ligand, so the fluorine right there is this R group right there, the fluorinated derivative, longer distance, probably a little bit too long for a real hydrogen bond, so it does not have a really tight association with the water. Okay. Now, let's look at the data for these two compounds and see how that demonstrates the difference in enthalpies in binding for these two compounds and also the entropies of binding for these two compounds. So, the fluorinated compound is a more potent ligand. And this was established multiple different ways. You have a thermal shift assay that's melting the protein, and if you have a melting point for protein and you then put a ligand in that protein that stabilizes the protein, you should see an increase in the melting temperature of the protein. Okay, so when you have a larger change in melting point, that means your compound is binding more tightly to the protein. Okay, this general feature can be used for lots of different assays, but this is what's called a thermal shift assay, and the fluorinated compound binds more tightly. So the dissociation constant was also measured, and you can see it's a more potent compound by almost an order of magnitude. Subsequent, now both of these, all this data suggests that the fluorinated compound is more potent. It's a better binding energy than the non-fluorinated compound. So, there's a study, ITC, isothermal calorimetry. It's pretty common in drug discovery and or enzymology that can measure the delta H and T delta S terms and differentiate those, give you quantitative numbers for those. That assay demonstrated that the delta H term for the hydroxyl-containing compound was much better. You can see that, almost 5 kcal per mole better. But the enthalpic term was better for the fluorine. And the change in enthalpy was sufficient to make the fluorinated compound a more potent compound. Okay? So the data is telling you that it's the entropy that's a lot better here, even though the enthalpy is better here in the hydroxyl. So there was a couple of other examples in this paper. I think this second example over here is a pretty powerful one in my mind. The difference is that in this side you see the symmetry in the two heterocycles there. Okay, both G's. That's this exact same example right here. You have G, G. If instead you have an A and a G, it's a different compound. But the overall trend is still the same. The fluorinated compound is more potent when you have the dissociation constant measured. The thermal shift is significantly different, and you can see delta G is definitely better for the fluorinated compound. When you break that down into the entropic and enthalpic terms, when you break that down into the entropic and enthalpic terms, it's shocking to me. This is crazy. The delta H of binding is actually positive there. But the T delta S term drives the affinity. and makes this actually a very, very, very potent ligand. That's crazy to me. Okay, so I think this is a cool example to study, read a bit more about, and see what the authors say about it. So I'd encourage any of the papers that I put up here, I'd encourage, to dig deeper if it interests you, but this is a pretty cool one. Very physical in its treatment. So I want to get through two sub-stories. This one will take a hint to develop. The second one's going to be quick, and then we'll break. So I'm shooting for 10 to 15 minutes for the tea break, and we'll be good. So you can ask questions about, well, if I have a methyl group, when should I put a CF3 there? If I have a CF3, when should I switch back to methyl? And there's a couple ways to go about the question. You can think about it a lot and try to convince yourself one way or the other. You can just make it. That's what I tell my group. Like, think about it, but also make it, because your thoughts might be wrong, okay? Try the experiment. Test your hypothesis. You're predicting that it'll be bad or better. Now you have to test it, right? So what we're going to do here is start asking the question, well, if I have maybe some crystallographic database or a binding model, and I have a methyl or a CF3 group, like, when should I put a little bit more effort into making the other derivative? What amino acids in the direct vicinity seem to favor one versus the other? And so this is a computational study here. Just to calibrate everybody with what we're going to see in just a minute, we're going to have red, blue, and green lines on a chart. It gets a little bit tricky when you have several lines on a chart. Those are just distances between the group and the amino acid that's in the vicinity. Red, blue, green. Okay. So you can see that the distances will be on the next slide. Now on the y-axis, you're going to see a ratio from the crystallographic database of, does the amino acid typically prefer CF3 or methyl? Like, if they just go in there and dig data out of the database, which one is common, which one is more preferred? Okay. And that's going to be a bar chart, and it's going to get pretty crazy. Now, this model evaluates and looks at electrostatic interactions and polar solvation energy. So polar solvation, that's like water, right? We were just talking about the entropic interactions, dehydration of a ligand, but electrostatic is also important there. Okay. So your slides are a little bit more complex right from the get-go, but I'm going to walk through it in a couple of quick steps here. So the first series of data is going to look at what happens under a distance of 3 angstroms there. And under 3 angstroms, you'll see a couple of amino acids that seem to have a very strong preference for a methyl group over the CF3 group. Okay, so you can, in this column right here, you're taking notes, you want to maybe jot down this. Under 3 angstroms, you have a methyl group, it's probably going to be your better choice. Okay, if you're leucine, your cysteine, your isoleucine. If you are under 3 angstroms and have phenylalanines, and maybe some other ones, but phenylalanine jumps out at you, man, I'm thinking about trying to get a CF3 into that space. Okay, statistically, that's favored. Not thinking about what interactions specifically ongoing, we're just looking at the statistics on what the crystallographic database says here. Now, as we get further away, that distance increases, 3 to 4 angstroms, a couple of other things jump out. Maybe in this region you had no preference, but now we have asparagine preferring the methyl, CH3 more common. You have a flip in selectivity, so if you get a little too far, phenylalanine no longer prefers CF3, now it's kind of preferring the other way, a little bit, slightly. Okay. So you get different trends as you move away. And so over here, these spots are just for you to look at that chart, make an analysis, and maybe jot down some notes yourself in your own free time. But note that there are some preferences that are distance specific. This is our, gosh, I'm trying to see, is that lysine? So this down here, so this is methionine, right? So our methionines, sorry, the angle I'm at, I'm having trouble seeing the difference between methionine and lysine on the chart. So our methionines prefer CF3 if you get just a little bit further away.
Cysteine does not, like, cysteine also has sulfur.
Yeah, it also has a SH versus a neutral sulfur. So there's a different acidification. There's a different environment there around cysteine relative to a methionine. Okay.
Yeah, something related question, because in these 20 amino acids, so when we are talking about CF3 or CH3 interaction with the amino acid, so but in the amino acid there could be CO, NH on the residue, or it could be anything. Is it like
This does not predict what the actual interaction is. This analysis doesn't consider that at all. It doesn't tell you what physical interaction is present between the ligand and the target. It only tells you that there's a trend, that the CF3 tends to be closer to that type of amino acid in the database.
But I still have, like for example, lysine. Lysine has the epsilon amine.
Mm-hmm.
So are we talking about the interaction of that amine with the CF3 or the, because then there is a
Yeah, so I think those are more the side chains that we're looking at.
Side chain.
Yeah, side chain preference.
Okay.
It's a model. There are lots of models. Ultimately, it takes a chemist, a person, a dedicated scientist to make the molecules and test them for your particular target. Okay? So that leads to this question. I thought you were going to this question. It's like, how do I know when I might have one interaction as opposed to the other? And ultimately, you're going to need like data and or crystal structures, docking model. Something's really going to have to help explain why you're getting changes in affinity. Okay, data is way better than modeling, but modeling is a great early estimate as you're going through a program, and they're great for predicting. But crystallographic data, cryo-EM, some measurement is always, in my mind, a little bit better than a model. Okay, models are very useful, nonetheless. So, in general, there's a nice series of papers from Anna Volpetti, who used to be at Novartis, maybe still is, I don't know. And they established a trend based off of NMR scores. So if you have more D-shielded shifts, you tend to have more of the hydrophobic or multipolar interactions. If you have more shielded fluorine atoms, as estimated by NMR, you tend to have more of the polar interactions, the one that look like H bonds, hydrogen bonds. So those are, it's a trend. It's a statistical analysis of the database. It does not always hold true for every example. Okay, this is just a trend, right? There's nice papers. When you go into this one, you do see a lot of pictures of what they're looking at and the type of geometries they're seeing. I've talked about most of those types of interactions, so I don't think it makes much sense to go re-look at those interactions. This is just looking at statistics and data here, okay? So it's a nice series, it's a nice paper to, again, calibrate yourself with. And again, these are evaluated by distance from the target and some other metrics too that might help you use it more intelligently in a campaign. Look like you're about to ask a question.
I feel like multipolar interactions are like stronger than the hydrogen bond.
Yeah, so the multipolar interactions, those were typically about a half kcal per mole. They can be a little bit stronger. The polar interactions that kind of look like a hydrogen bond, again, the rough estimate is less than 2. That doesn't mean 2. It doesn't mean 1.5 or 1. It's just less than 2. It might be 0.3, 0.5, okay? So they vary, but they are still reasonably small. They're nowhere near as strong as your typical hydrogen bond that you would anticipate from a good hydroxyl group or appropriate NH or an amide linking onto something properly. Okay, so just a little bit more comments. I've commented on these things in the previous slide, but just a little bit more text that supplements what I said. I think this is mostly redundant with what I've said, but just for your own notes. So this is the point that I thought was going to be 11:10 to 11:15, but it's 11:08 and 45 seconds. Can we still break now? Is that okay? I think it's a good point for a transition before we get into the last few slides.
He should be there in 5 minutes, so before that they can have a small break.
Is that good? Okay.
So
We come back at 11:25.
yes, we can back.
Is that still good? 11:25 we can come back?
Yeah, but I still have one point regarding.
Oh, yeah,
this.
one more question,
Because
comment?
When I was I was going through some of the literature, because these one paper which I cited in my slide, it was telling still that most of like CHF kind of interaction was like predominant whenever they are observing. So I personally thought that when we are planning, as a chemist is planning to incorporate fluorine, so what I took a message on, and also some little bit from your like last 2 days of teaching. What I thought maybe depends on the if we are more into hydrophobic pocket, and you want to have a check the fluorine presence, maybe then if it is hydrophobic pocket, then we should have a different plan. If it is if it is a hydrophilic pocket, then we should have a different plan. Like from your previous slide, you had that all interaction together. So maybe we can thoughtfully incorporate changes based on also the what kind of pocket like our residue is lying. So will that really help?
I think that's true for all medchem, that you should always be thinking about what's the nature of the amino acids and opportunities to develop your ligand or design your ligand. Like you should be thoughtful about the pocket and what's there, and then try to design things in that seem reasonable. Also think broadly, and one derivative doesn't always test your hypothesis well enough. You might need to make 2 or 3 derivatives. It also helps to have 2 or 3 hypotheses. And so, maybe it's more of a hydrogen bonding interaction that we can get. So we want to make a couple things that have more nitrogen oxygen in that vector. Or maybe instead we can get more of a polar interaction. So we need fluorine, which is going to be stronger as a dipole. And that might be the better one. So, it's the same residue that we're trying to get to, but we can get through it through an electrostatic interaction or a hydrogen bond. Or maybe there's something just next to it that we might also be able to engage. So we should think, instead of just ortho, we can go over meta and try something else. So, I think having several hypotheses is always good.
Yeah.
Yeah.
So I think this is very important. When we are trying to do medchem and we are 2 to 3 hypotheses, and again for each hypothesis 3 to 4 variables, so that we can actually test our hypothesis. So I think that is what I think should be a good idea.
Yeah. Okay. Good. We'll break for a bit. We'll be back in a little bit.
reaction of the fluorine chemistry Pg. After that, we will have a talk, which is an open talk. So which many other students will also join. Let's
Okay, so time to get back going again. We'll jump back into this lecture, and we're just about to transition into a newer type of bonding that's been recognized that for which fluorine is, can participate, and that's called tetral bonding. The name looks kind of funky. Tetral, tetrahedral, tetrahedrons maybe have something to do with it. Okay, so let's go ahead and start looking at the basic principles of this type of bonding interaction. Tetral bonds are a little bit more general than just a fluorine-specific substructure. So we'll describe the initial phenomenon first. In the general tetral bonding interaction, you'll have, there's my pointer, you'll have some type of atom. You can see the nature of those atoms there, all vertically, right? Yep, it's a single column there. They're tetrahedral in geometry, roughly tetrahedral, attached to 4 different groups. You have some type of a carbon-based group there, and through a charge transfer interaction, lone pair of electrons on some type of nucleophilic species can donate in. So what's going on in this system? You have a difference in electronegativity between your substituents and the heteroatom that generates partial cationic charge on the heteroatom, but you also have a sigma hole presented. And that sigma hole can interact with pi systems or lone pair of electrons in that charge transfer type interaction. We've seen similar interactions before. We have like a carbon iodine, carbon sulfur bond, like those are those type of halogen bonding interactions. In this case, the fluorinated, the CF3 group, it's the fluorine atoms that promote formation of the sigma hole. Okay, so this is a unique interaction. You can see the CF3 group, I've drawn that down on the bottom. The fluorine atoms being electronegative, pull electron density away from carbon. You get delta plus character here in the sigma star region, and then nucleophilic lone pair of electrons can donate into it. You can see the distances shown there. 2.5 to 4 angstroms. The angle, the geometries are pretty important here. In general, the angles are close to linear between whatever the nucleophilic atom is and the CR bond. That's close to 180. There's some deviance, there are outliers, but you want to be thinking of a roughly linear arrangement there. And these are not the strongest bonding interactions, still less than 2 kcal per mole, but that can still give you a benefit in a drug discovery campaign. So here's just a little bit of a visualization of what a tetral bonding interaction looks like, or the sigma hole specifically. When you have a model system, you'll see you have delta minus character in around the fluorine atoms and a little bit of cationic charge. This is for aryl ring, a trifluorotoluene that has a hydroxyl group at the para position. If you have just a neutral species, trifluorotoluene, a little bit bigger of a sigma hole. And in this case, the sigma hole is a little bit more pronounced because the other fluorine atoms on the rest of the ring are further amplifying the size of the sigma hole. Okay. So that's what's going on there. There are a series of nice studies describing the physical chemistry behind this phenomenon, as well as demonstrating how it applies in drug discovery. So we can look at a couple of examples here. This is an example of a ligand that is making a tetral bond. The crystal structure that we've reconstructed and refined is shown right here. The distance of that interaction is 3 angstroms in this case. It's a nucleophilic oxygen presenting in to the sigma hole. You can see the angle there, not quite linear, but not far from it. And that's been computationally recapitulated through an analysis of non-covalent bonding interactions, in which you can see interactions in the modeling there. Okay, so these NCI analyses can be done. There's a little bit more information in the reference. But when you're looking at a crystal structure, trying to say, hey, am I able to exploit one of these rationally? Or if I have some type of a CF3 in my molecule, is it making this type of interaction? You have the general trends on the previous slide of what you should be looking for, the distances and the angles there, and you understand the basics of the physical phenomenon. Here's another example. Maybe first I'll say this was a side chain, aspartate presenting in, so you had an anionic functional group presenting in towards that sigma hole, and you can also have neutral species. So this is an example of a backbone amide that's nucleophilic at oxygen, forming a tetral bond with the CF3 group, and that's shown over here. Okay, you have the carbonyl lone pair of electrons presenting down in the distance there, 3.6 angstroms, a little bit longer, still nearing 180 degrees there, 167, that's still within the acceptable range. And again, an NCI analysis also demonstrates computationally that there's an interaction there between the carbonyl and the sigma hole of the CF3. Okay? So those can be exploited. You have to have the geometries right, you have to have the distances right, but that's also true for a lot of the other interactions we've been talking about. But this is a unique one for the CF3 group that can be exploited. So those are all favorable interactions, but fluorine, it can also resist certain functional groups. There are also fluorophobic environments for which it would be less favorable to present a fluorine or fluorinated substituent into this type of fluorophobic environment. So maybe we can summarize those briefly. Now, to summarize those, I want to come back to this original example from Francois Diederich's group. And I had mentioned before that there were certain derivatives that were less potent than others, than the core structure. And so that's shown here. Compound 1 is the non-fluorinated derivative. 2-fluoro, 2,6-difluoro, 3,5-difluoro. These are all less potent compounds. So you're presenting the fluorine into the wrong vectors, and further analysis identified certain reasons why that happens. So what should you not do? What are the fluorophobic type of environments that we should typically try to avoid? Well, if you have a CF bond and you have a lot of other electron density there, it's already a polar environment, you don't want the wrong ends of magnets presented towards each other. So if you have a CF bond that's electronegative and delta minus over on fluorine, and you have a CO bond that's delta minus on oxygen, it's not going to be favorable to have those things presented towards each other. Okay, you know that from playing with magnets as a kid. So that's not favored, as well as other dipoles that might be inappropriately aligned. So fluorine presenting towards pi systems. We know that pi systems typically have delta minus character in the pi cloud above and below the plane of the ring. Okay, for most systems, it's pi rich there. And you don't want the delta minus of that dipole to be presenting towards other anionic moieties, such as a pi-rich ring. Makes a lot of sense, right? So watch out, avoid that, and then the dipole alignment, that's another general principle that we should avoid. So here's an example of a study in which the group had been looking at some inhibitors of this enzyme. You can see that the structure here, the crystal structure, has some of the distances, and the disfavored interactions in this case have the fluorine atoms presenting into the pi systems. And you can see those here, distances here of 3.7 angstroms, that's kind of over the pi system. Here you can see 3.4, 3.7 angstroms, and again, those are systems in which the CF bond is kind of presenting in towards the pi ring. It's sometimes tricky to see in 2 dimensions, but you can further study this if you would like. Okay, so that's what's going on here. You have other disfavored interactions going on over there, and so those were all determined to be disfavored, and this was the main takeaway, the main message. Watch out for that CF presenting into pi systems. Okay. It's a hydrophobic environment. You can see all of the greasy moieties here, a couple phenylalanines, a tryptophan that's pretty greasy. But even though it's greasy and it's hydrophobic, you're presenting the fluorine at the wrong distances and the wrong vectors in this system, just based on the geometries presented in the pocket. Okay. So cautious about that. It can go the wrong way if you're pushing fluorine into pi systems. Okay. So those are some of the key things to watch out for. Things can get worse. We saw that initially in the multipolar interactions. Like we had that bin of compounds that statistically get worse when you put fluorine in there. Okay, that's another reason why here. So let's go ahead and look at some other types of molecular interactions for which fluorine is perturbing some other functional group and the interaction that it's making with a target. Okay, we'll see several different examples here, and we're going to be comparing maybe some charged species interacting with carboxylates. We'll also see how acidification of CH bonds can occur through fluorination, and then maybe we can drive affinity through a CH bond making an interaction with a Lewis basic set of lone pair of electrons from the target. So this is a really nice modern classic example of fluorination modulating the affinity of a drug to the target and being exploited to improve the toxicity of an important drug. So this compound itself is fentanyl. It's a mu-opioid agonist. It is a super potent compound. It is a painkiller. It's also one of the ones that's super addictive and super deadly. Okay. With the mu receptor, the respiratory depression is particularly deadly. They have reward. They're rewarding drugs, so the addiction is real to these things. But the respiratory depression is what's really problematic. So the drug structure itself has a basic amine. You can see the pKa there at physiological concentrations. That's going to be predominantly protonated. That amine is essential for engaging the mu receptor. So the electrostatic interaction between an active site aspartate and the protonated form of the drug drives affinity pretty significantly. Now, in the series of compounds presented in this paper, a series of fluorinated derivatives are introduced. And when you fluorinate, you change the basicity of the amine. So instead of having a pKa of just over 8, your pKa is now below 7. And below 7 means you're predominantly neutral under physiological conditions. So when you're neutral under physiological conditions, you do not have this electrostatic interaction that drives affinity for the receptor. So this compound is not going to have affinity for the receptor when you have the wrong pH. But under acidic conditions, as the pH rises, perhaps because of cell stress or some other thing going on in the cell, you can have increases in cellular pH. Then we protonate, then you have affinity for the receptor. So we now have a drug that will engage the receptor in more acidic media and more acidic cells. It will not engage the receptor as well in more alkaline cells. Okay. So that's a feature that was further studied and validated. I'll start over down here with mu-opioid receptor affinity. This is for the drug, the parent drug that just has a hydrogen in it. So that's the one that has a pKa just over 8. At pH 7.4, it's protonated predominantly. So the data that you're looking at here is potency data, Ki values as a function of pH, and for practical purposes, these are all the same values within air. Okay. There's no change of potency in these drugs as you go from pH 5, 6.5, and then physiological pH at 7.4 there. The bottom of these curves are within error. There's no change in the efficacy or potency either way. In contrast, for the fluorinated compound, you do see a potency shift as a function of pH. So at acidic pH, you'll see the Ki value, 7.3. See big error bars there, 2.6. So recognize there's big error bars in that measurement. At pH 6.5, you have essentially an equipotent compound. Again, because of the error bars here, these are like basically the same number. Okay. In contrast, as you go to neutral pH, at neutral pH, the fluorinated compound is less protonated. Remember, it's an equilibrium. So the amine is less protonated, and you start to lose affinity. You can see dropping down to about 18 there from single digits. Okay, so they're exploiting the difference in pKa between the two ligands to drive affinity in cells that are acidic, but lose affinity in cells that are less acidic. And in this case, under stress environments, certain CNS cells are acidic. So we can selectively get the drug to activate and engage the mu receptor in acidic cells, okay? So their in vivo efficacy was established in multiple models of pain, heat sensitivity, mechanical hyperalgesia, non-inflammatory and inflammatory pain models. There's a lot of different types of pain, right? The receptors, when you poke yourself with a needle, are not the same ones that are activated when you have a burn. Okay, and they're not the same ones if you have like arthritis. Okay, there are different types of pain, and different pharmacological targets might be better for different types of pain. Okay, nonetheless, this was evaluated in several different types of pain. It's important to think about the adverse effects, and can we modulate the adverse effects that can be come from peripheral activated mu receptors. So reward or addiction, that was modulated. We have minimal reward. We minimize reward potential when you have the fluorinated compound. These opioids, these mu opioids, they promote constipation. So you have mu receptors in the GI tract, and you take mu agonists, you typically get constipated. That you can see the number of defecations decreases when you're on the parent drug, but there's statistically no difference. They seem to be pooping perfectly fine when they have the fluorinated version of the drug here. Locomotor control is better with the fluorinated compound relative to the protonated compound, and they seem to, again, move around the cage reasonably well. They're not lethargic when you have the fluorinated drug relative to the hydrogen-containing drug. Okay. So they are generally safer. These are particularly important because this is what is toxic. This is what's deadly, what's lethal for these drugs. The respiratory depression, losing oxygen in your system, decreased heart rate, that's what kills people when you take too much of these things. And this compound did not affect those as much as the parent compound. Okay, so cool story there. Hopefully more might eventually come from that strategy. But the mu receptor is really tough to target and target well, even though we have several drugs that do hit it. So another fluorine-induced phenomenon is the acidification of geminal CH bonds. So the acidity can actually replicate in some conditions the acidity of a phenol. Okay. And that's going to be the signal withdrawing effect of the fluorine atoms pulling electron density away from the carbon. As a result, the carbon, it still wants electrons, so it's going to be pulling electrons out of the CH bond towards itself. And that's the nature of the acidification. It has been studied in a couple of systems. Some say it's a stronger interaction, some say it's not quite as strong. So there's disagreement in the literature about how powerful is this interaction. Nonetheless, you can see in the OH bond, you have your oxygen, you have your cationic hydrogen. Here we have our CF2 that has a lot of delta minus character, and the corresponding hydrogen would be out over in this space over there. Okay, and you can see the blue coloring and the red coloring in similar locations in those two structures, in those two computational models. And these have been further studied. One estimate based on this really cool supramolecular arrangement estimates the energy associated with the OH hydrogen bond to be about 3.5 kcal per mole. And in this case, you have a nitro group making an intramolecular hydrogen bond and an intermolecular hydrogen bond there. You can see this network having about 3 kcal per mole in energy. So this estimate says they're pretty close in hydrogen bonding potential and hydrogen bond strengths. One other thing to think about here is other changes in the molecule. So even if maybe you lose little affinity, can you still have a better molecule overall for your discovery process? Let's think about the rest of the pi system. So if we're thinking about oxidative metabolism here in this case, we have a more pi-rich system with the phenol, and the CF2 is pi deficient. Maybe you'll have less arene oxide formation, less hydroxylation of the aromatic ring using this substitution relative to that substitution. Maybe that compensates for a little loss in potency. In contrast, or in addition, that hydroxyl group can undergo the conjugative metabolism. It's nucleophilic. You can conjugate on sulfates and glucuronides and other things onto this substructure, this phenol. You're not going to do that over here. This is not going to undergo conjugative metabolism. Pretty powerful difference for PK properties, perhaps, if you use it properly. Okay. It doesn't always work. You can't always get a phenomenal hydrogen bonding interaction with this substructure, but sometimes it works and works great. So, a second study, a more recent study here, suggests that this is not actually a very strong hydrogen bond donor. In this study, they used that NMR strategy that I had mentioned previously. I said there's a mathematical equation I'm going to show you. You just have to wait for it, and here's the equation. The paper that has this equation, description of the assay, is on the other slides that we had before. Okay, but even if you go to this this paper down here on the bottom, they cite the right one anyways. Okay. So the strategy for measuring this, again, involves measuring the difference in the shift of the proton when you measure the NMR in DMSO relative to chloroform. Okay, and the difference in shift estimates how acidic that hydrogen bond is. And you can do that with phenols and alcohols, but you can also do it with some of the CF2 bonds. And we'll look at a little bit of the data there. So in the phenols, here's A values suggesting that these are reasonable hydrogen bond donors. Just for a comparison, if you have like toluene and you know, what is this, ethyl propylbenzene here, you can see negative A values. Those don't hydrogen bond well with DMSO or chloroform, right? But when you go over to the CF2H on the other side, you'll see the magnitude of the A value is significantly lower than the magnitude of the A value over here, about 10 times weaker. Okay, so this estimate is saying, these are pretty minimal, it's not very acidic, it's not very good for drug discovery. Nonetheless, they can have profound effects, and so here's a series of molecules that has progressed into a clinical candidate. In this early series, we have an NAS3 protease inhibitor. You saw one of these other molecules when we looked at the metabolism. We had a big heterocycle here. All of this substructure is the same. You actually had this linked over here. We did geminal difluorination, and then we also had a moiety, I think it was dangling off of this position here. That's the vinyl group, and then we looked at a bunch of fluoroalkyl derivatives coming off of that position. But the target here is the same target as we had already looked at. And again, when you look at the slides and look at the drugs, like scream out at it, like, yeah, these are the same target, okay? The NS3 compounds, like, they all look very, very similar to a medicinal chemist. Okay, so in this series, we're looking at inhibiting replication in a biochemical assay and then a cellular assay here. So that's why you see more potent compounds in the biochemical assay relative to the cellular assay there. The specific series of compounds will have a cyclopropyl methyl, difluoromethyl, and trifluoromethyl. The potency of the compounds increases over 10-fold as you go from methyl to the CF2H. The CF3, when you put the CF3 in there, you lose potency. You know, no beneficial interaction relative to methyl when you go to CF3. Okay, so there's something about having a CH there that's useful, that's helpful, and this data is also replicated in the cellular activity. And the crystallographic data indicates or suggests a CH bond. That CH, that's the CF2 right there, and then this is the CH bond presenting down and making a hydrogen bond. I didn't remember off the top of my head, that's 2.5 angstroms there for the distance between that CH and the carbonyl. Okay, so within the distance you would expect for a good hydrogen bond there. And so maybe in some cases it can be useful, it can be beneficial if you get the distances right and you get the angles right. Okay, so it can be used, it can be exploited. Again, the model systems seem to disagree on how powerful it can be. The medchem evidence suggests it can be useful. Okay. So we're going to look at another really, really unique example of model system. Yeah?
But sir, in previous slide, there were also chances to get that one, that CF3, where it is attached to that cyclopropyl ring, that is rotatable, right? That one is rotatable. So
Yeah, so you're saying
if
if this is CF3, that's, okay, go ahead.
Here there were chances that fluorine can have an interaction with that carbonyl as well.
Yeah, I think what's going on here, so I'm going to stay on the mic over here, try to talk from over here. So the CF3, if you had a fluorine here, that's actually closer to the carbonyl than it is to the carbon. And if you put the CF3 presented towards the oxygen of the carbonyl, sorry, it's close to the oxygen of the carbonyl. So if you present the CF3 towards the oxygen, you have delta minus character here and delta minus character on the oxygen, and that's repulsive, and that's recapitulated in the data, or the data supports that. When you go from a methyl to a CF3, it's worse. Okay. Now, if you had a dipole interaction, or the multipolar interaction that we were talking about right at the beginning, the first interaction we were talking about, you would need a fluorine atom closer to the carbon, not closer to the oxygen. Okay, so think about that. If you're like this, that's bad, but if you place it there, it's good for those multipolar interactions. And I think that's what you're thinking about. Okay. Is that fair? Okay. So the distances matter, the angles matter, the geometries matter. You can take something repulsive and make it attractive. Maybe if they could reach a little bit deeper into that pocket. I don't know what's closer to us, like how tight that pocket is. I don't know what else they did. But this, progressed on to a clinical candidate. So, yeah.
About this, again, I have one doubt and also a comment because I think somewhere I read that, and also I mentioned in my talk that, or it is actually mentioned by an author in the paper because I'm not a student, that mostly the driving interactions are hydrogen bonding, the typical hydrogen bondings, and these are the add-ons.
These are the what?
Add-ons, which adds to the overall stabilization of that receptor ligand interaction. So, because for example, in this interaction, there could be adjacent hydrogen bonds which has already locked.
Oh yeah, absolutely.
And now your CF and because now there is no much room for the molecule to turn and make conformational change, so that they can because going from near oxygen to near carbon in the carbonyl could be possible by conformational change, but now that is not being allowed because of the other interactions in the molecule.
So you are relying on the rest of the system. Is my clicker? Okay, there. So you are relying on your heterocycle and this over here and this stuff. You're relying on that to drive affinity. Right? We're already at a 10 nanomolar compound. There are a lot of other things that are well positioned in this molecule that are driving the initial affinity. And this is gravy. This is great to get this jump, this boost, but all the other interactions are giving you a 13 nanomolar compound to start. Right? And I think that's where you're going. This is late stage fine tuning, improving interactions, but you have to have everything else set up so that you can see these types of boosts later on. If you're using this type of interaction to drive affinity from the outset, it's going to be tough. Yep. Okay. So this is a really fun story on fluorinated ketones. Fluorinated ketones have unique interactions with biological systems. And in order to understand this, we need to go back to some really, really basic physical organic chemistry, ask the question, what happens to carbonyls when you have electron withdrawing groups attached to them? So we're going to, for teaching purposes, we're going to just think of like an aliphatic or diaryl ketone and what happens when you put a strong electron withdrawing group next to it. Okay. It turns out that the strong electron withdrawing group prefers to, it encourages the carbonyl to rehybridize. So you go from an sp2 state to an sp3 state. Okay, and that happens because the sp3 hybridized state allows electrons to distribute towards the electron withdrawing group. Okay, this is a phenomenon that was described by Bent. Basically what's going on here is when you have sp2 hybridization, the contribution of this bond here from the carbon atom, it's an sp2 orbital, 1 part s, 2 parts p, a little bit shorter. The carbon is a little bit more electrophilic. The carbon in CsP2 is pulling its electrons, holding its electrons a little bit closer to itself. When you rehybridize to sp3, now we have 1 part s, 3 parts p. Those orbitals are a bit longer. The carbon allows the electrons to drift closer to the electron withdrawing group because those orbitals are a little bit longer, a little bit bigger. Okay? So it's a better electron donor into the sigma bond when you have a CsP3. In this case, we have CsP2, it's more electrophilic. We have an electrophilic carbon next to an electron withdrawing group. They're playing tug of war for the electrons. There's an electronic argument going on between those two. They both want the electrons more. Again, rehybridization allows the carbon to share its electrons better with the electron withdrawing group. Now, the electron withdrawing group, for purposes of this class, CF2, it's going to be a fluorinated group. And so let's go ahead and think about what's going on. In order to go from CsP2 to CsP3, we need some type of nucleophile to add in. It could be an alcohol, it could be amine, it could be water. Okay. When that happens, that's going to require the attack of that moiety onto the carbonyl. Okay. When you have the carbonyl and you're thinking about the LUMO of the carbonyl, the HOMO-LUMO energy gap is going to be smaller when the alcohol attacks the more stabilized carbonyl, the carbonyl that's lower in energy, it has a lower LUMO. Okay. So that's one feature. There's a kinetic preference for nucleophiles to attack these fluorinated ketone derivatives. But the other one that I was telling you about before is a thermodynamic argument in that there's a difference in the hybridization of the two orbitals. The CsP3 hybridization state allows electrons to flow towards the delta plus more readily. Okay, so it turns out that this substructure has been exploited for biological probes and therapeutics regularly enough. I'm going to put a couple of examples up on the next slide that are going to involve proteases, serine proteases, and aspartate proteases. Serine proteases, they cleave peptides, right? And the catalytically active species in a serine protease, it's going to be a nucleophilic serine hydroxyl group. Now, there are going to be other amino acids in the enzyme that help activate and stabilize the transition state. So again, think about the hydroxyl group attacking the carbonyl. When that happens, you generate the tetrahedral intermediate, and then you need stabilization of this species. And that's what some of the other residues in the catalytic pocket are doing. Ultimately, collapse of the tetrahedral intermediate will cleave off an amino acid, and you can ultimately regenerate the catalyst system. And in this case, you can use fluorinated peptidomimetics to make reversible covalent inhibitors. Reversible covalent inhibitors. What does that mean? Okay, so in this system, you can see how the CF2 group is introduced into the ketone. When the serine hydroxyl group attacks, we've now made a covalent bond between the drug substance or probe and the enzyme. That transition state, that tetrahedral intermediate, will be further stabilized by the other residues in the active site. But the drug itself cannot float away until the tetrahedral intermediate collapses. But when it collapses, it cannot cleave. You don't have the carbon-nitrogen bond here. See here, when we close that tetrahedral intermediate, we kick off the amino acid. In this case, you're kind of stuck there. Okay, so it's a covalent inhibitor, but it's also a reversible inhibitor. It's a really cool strategy for going after serine proteases. Now, there are other classes of proteases, and some of those can also be targeted by these fluorinated peptidomimetics, these fluorinated ketones. And aspartate proteases are also another example here. So in aspartate proteases, you have different amino acids in the catalytic site responsible for activation of the correct peptide bond. And so in the aspartate proteases, you have two aspartates. One of them is making a hydrogen bond with the appropriate site of the peptide that you're trying to activate. The oxygen is bridging over to water that bridges over to the other aspartate. So what you have is a highly organized system in which we're activating the carbonyl, but also recruiting water and presenting water at the right vector to attack the carbonyl. Okay, so you have activation of the substrate here, you have activation of water and recruitment of water. And when water attacks the carbonyl, you make a really nice tetrahedral intermediate. Look at the beautiful stabilization, hydrogen bonding network there. A really nice organization. Nature figures how to do really cool things sometimes, and this is one more example. Collapse of the tetrahedral intermediate ultimately cleaves the peptide at that site, and you still have the aspartates there. Now, the fluorinated peptidomimetics can also inhibit these enzymes, but in this case, it's not a covalent inhibitor. It's an inhibitor in which the substrate will still get recognized by the enzyme. It can still get activated by the aspartate, and the delivery of water generates this really beautiful network there. And that's a stable network. It cannot cleave. Again, you don't have a CN bond here. You have a CC bond. And so you kind of get stuck in this state in which you have the CSP3 hybridization that the fluorinated ketone wants anyway. It's more stable in that hydrate state. And then you have the really nice hydrogen bonding network that can really drive affinity. Okay, so let's see a couple of examples of how this plays out in biological probes. The first series is acetylcholinesterase inhibitors. Acetylcholinesterase is a serine protease. The endogenous substrate is shown here. The affinity of the substrate for the enzyme in this case is heavily driven by the charge. There's an anionic residue in the active site of the enzyme that recruits this cationic amine. If you get rid of the cationic amine, you really lose affinity, big time, right? Yeah, we're nanomolar, 300,000 nanomolar. It's not very good, right? So if, in this case, we've taken the charged amine, we've replaced it with a T-butyl group. We can regain a massive amount of affinity by introduction of fluorine atoms on either side of the carbonyl. If we put it over here on this side, a trifluoromethylketone, look at that change in affinity. Wow. And if you have two fluorine atoms on the other side, you have this internal difluorinated ketone, you drive affinity even further. Now the difference is that there's a little bit of steric congestion when you have the bigger CF3 group on the side. The enzyme typically recognizes it as an acetate. The acetate has a little methyl group right there. Okay, so the pocket isn't outrageously big. The CF3, it's just like, it's a little too big to fit in there perfectly. But if you bring the fluorines back over to the other side of the enzyme, I mean, look at that affinity, like 300,000 to 1.5, 1.6 with two fluorine atoms. That's pretty dang cool. Okay, let's look down at the second example. The second example, it's still cool, maybe not as cool, but it's still pretty cool. This would be the example of a couple of probes and some data in terms of how they engage aspartate proteases. I'm going to start over here with this one. This is the fluorinated ketone. This one over here is an alcohol, and I'll do a quick comparison with that one in just a minute. So for the ketone, again, the aspartate mechanism, let's quickly review that. Here it is. We're thinking about this type of an interaction there, okay, that type of a network, and the fluorinated ketone can facilitate that network. When you go from the HH ketone to the difluorinated ketone, look at the difference in potency there, 134 to half. It's pretty good. It's pretty good change when you can use that properly. In the other case, you actually see that the fluorinated compound is less potent. What's going on there? Well, this is a case for which instead of a ketone, we have a hydroxyl group. Now that hydroxyl group, I'm going to go back a slide just to remind everybody what's going on. If you have a hydroxyl group at this position, we can only make one of these hydrogen bonding interactions. We can only get one of those. We can't get both of them. Okay? So if we have a single hydroxyl group, we can still ask the question, well, if we have a CF2, how is the CF2 going to perturb these types of interactions? Okay. And you know this. We talked about the basicity and acidity changes that occur. So you can go back to those tables if you want, or you can just think for a minute. Well, if we have a hydroxyl group, the OH bond is going to be more acidic. Okay, if it's more acidic, that's the hydrogen bond donating potential. It's going to be better, but we're going to be less basic for the lone pair of electrons. And if we're losing affinity, maybe it's the loss in basicity of the lone pair of electrons here in engaging the receptor, or that hydrate-like form that we saw in the previous slide. Okay. So if we have a ketone, we're rehybridizing really beautiful interactions there. If we're at the alcohol, we're just perturbing the acidity and basicity of that functional group. In this case, you lose affinity for the receptor. Okay, cool example. Basic principles explain it all, right? You just go back to those perturbations that I kept beating into you early on, and now it hopefully helps. It pays off eventually. So these types of this substructure, this moiety, has been used to modulate a wide variety of different enzymes. You can see lots of disease states. You can see serine aspartate proteases, other popular targets that have been drugged over the years, diuretic type activity. This is a really fun one. I should probably make an example of this one for like the tutorials. But this is a beautiful one for conformational control. Because what happens in this case is you have an alcohol there, and the nucleophilic alcohol will attack the carbonyl and make a hemi-acetal, hemi-ketal type substructure, and that's stable because it wants to exist in the CsP3 form there because of the fluorine atoms. So it's a control element for having this thing cyclized down into a ring. It's pretty cool. Okay. So I have one more phenomenon to talk about in this series of examples by which fluorine can modulate the reactivity between a small molecule and a biological target. And it's going to be in the area of phosphates and fluorinated phosphate mimetics. So phosphates, super important for biology, chemical signaling. Kinases transfer phosphates from enzyme to enzyme to enzyme for signaling. We know phosphates can activate nucleosides. The nucleosides themselves, so that primary hydroxyl, need to be phosphorylated and then diphosphorylated and triphosphorylated before they can get polymerized. We saw those cyclic nucleosides, cyclic AMP, cyclic GMP are important chemical messengers within the body. Those have a phosphate bridging two nucleosides. Okay. Phosphates are super important. There are enzymes that put on phosphates, the kinases. There are also enzymes that remove phosphates called phosphatases. They can also hydrolyze under the right conditions, okay? So phosphates going on and off of biological molecules has a really, really, really profound effect on physiology, biology, cellular enzymology. Okay, so that these enzymes can go on and off. They have certain acidities associated with loss of one or both protons. You can see the pKa's there, very close to phosphoric acid. Now, in order to generate biological probes or therapeutic candidates for which you can engage the enzyme with a phosphate-like substructure without having the liability of that phosphate falling off, we can use phosphate mimetics. And one common strategy is to introduce a carbon-phosphorus bond. That carbon-phosphorus bond can't cleave. And when it engages the enzyme, you still have these three the two acidic OHs, the phosphate, and then a third oxygen there. So you can see how maybe in the pocket of the enzyme, regardless of what pH you're at, you might be able to mimic the interactions. Now the challenge here is that the pKa's are different, oxygen being more electron withdrawing, carbon being more electron donating. You get roughly a log difference in pKa, so they won't be anionic or dianionic under the same conditions. But we can use fluorine to modulate pKa's. Electron withdrawing group, that effect can acidify the OHs on the phosphate. So I'll introduce briefly a couple of different derivatives. You can use a monofluorophosphonate that brings the pKa very close to a phosphate itself. That would be what we call an isoacidic variant. If we really need that phosphate to have the same charge as this one, we can use a monofluoromethylphosphate. Now, this is a stereocenter. You have to be thinking about two different isomers. Maybe that's important for your target, maybe not. But you have to watch out for the stereochemistry there. Now, this oxygen introduces a dipole into the molecule. And if you need a molecule for which you need the similar polarity overall, you can use the CF2. The CF2 mimics the dipole of the oxygen better. The carbon-fluorine bonds present at the same vectors roughly as the lone pair of electrons. So that's what's going on there. This is an isopolar mimic. It's a little bit more acidic. We have an isoacidic mimic. And then the CH2. Remember, fluorine atoms are really big, right? They're not H's, right? They're bigger than H. We established that on slide number 1 of this entire thing. Okay. So this is a bigger functional group. If you want it to be isosteric, the CH2 is the one that mimics the size of the phosphate better. Okay, so you have a couple of different derivatives there, and these have been used pretty broadly in chemical biology. A lot of times if you're trying to take like a phosphopeptide, you don't want that phosphate to come off, and you just want to see the activity, like when it's phosphorylated, what happens. This is a great strategy. Okay. So, hopefully the key points have become apparent. There are several examples that we've looked at, but you can use fluorine to modulate acid-base chemistry, and that can subsequently affect engagement interactions with charged residues and molecules. You can also modulate other interactions by fluorinating and perturb those interactions. Let's come into the end of this lecture. We're also very close to the end of like all the coursework type lecture. As much as possible, I'll keep reminding everybody to be a master of the physical organic chemistry and think about the really basic principles and how they apply and how they influence all of those drug-like properties. The drug-like properties are ultimately what you're measuring to say, is this compound going to be good enough to put in my cellular assay, in my in vivo assay, and ultimately someday a clinical candidate, hopefully from some people in this room. This is really important stuff, but the basis for everything we're studying here is physical in nature. So if there's like one key message, make sure you're really strong in physical organic chemistry, understand the molecular interactions, think about thermodynamics and kinetics and all those things. It's going to apply in biological settings further down in your careers, okay? So, that's it for today. I think we're breaking for lunch. It's 12:25 and we're kind of shooting for 12:30, so I think we're close enough. And when we come back, it's going to be more of a scientific lecture, and I need to go make a boatload of adjustments to my slides because it's a 2-hour time block, and so it's going to be an interesting one. So, anything else? What time should we be back? Or
Yeah, so I think we have some time, so try to make sure that you do the Yeah. So good afternoon all. Welcome back to the last and very special lecture by Professor Altman. So because I can see there are many members who are not came just for this lecture, and so I just wanted to tell you a brief about Professor Altman and also about the GIAN course. So Professor Altman is a full professor and holds Stephen Lee and Taglian Chair in Pharmacy with appointments in Bosch Department of Medicinal Chemistry and Molecular Pharmacology, and James Tarpo Jr. and Margaret Tarpo Department of Chemistry. Dr. Altman received BS Chemistry from Creighton University in 2003 and PhD in Organic Chemistry from MIT 2008. Studying as a Pfizer and National Institute of Health postdoctoral fellow in Professor Buchwald's laboratory. He subsequently trained as an NIH postdoctoral fellow at Professor Larry Overman at UC Irvine, and then joined Department of Medicinal Chemistry at the University of Kansas as an assistant professor in 2011. During this time, I was a postdoc over there, so I got to know Professor Altman. And because of that association, we wrote like a GIAN course. It was actually a teaching course which he has already delivered last 5 days. It was just completed before lunch. And because I just wanted to benefit many of the student research scholars who could not attend this course, so I requested him to give a lecture on his research, what is going on. And he has very kindly agreed. This is a very special lecture because it's a 2-hour lecture. So we will be taking maybe a 5 minutes break in between. Okay. So after working at KU for up to 2017, he moved to Purdue University. In 2017 at KU he got associate professor. And then he moved to Purdue University as a full professor in 2020. The Altman's group works at the interface of synthetic organic and medicinal chemistries with synthetic emphasis in the area of organometallic and organofluorine transformations, and with collaborative medicinal interest spanning a range of diseases including pain, anxiety, mood disorders, aging, and immuno-oncology. Professor Altman has taught a variety of topics at the undergraduate, graduate, and professional levels, including organic chemistry, medicinal chemistry, biochemistry, and a broad range of therapeutics area. Dr. Altman is a chair of the National Institute of Health, Chemical Sciences, and Biosynthesis Study Section. So, Professor Altman, we really enjoyed the kind of teaching course he has delivered, and we are really looking forward to your this special lecture for all the students. So, with this, I invite Professor Altman to deliver this talk.
So hello again, everybody. Welcome back to those of you who have been here all week. Welcome to some of the new individuals here who are here for the first time. I'm happy to continue to share science in this last little stint. It is a 2-hour lecture, as mentioned, and I've actually never given a 2-hour lecture, so the estimate of time is going to be, maybe a little bit off. We'll find a nice time to break, just to get a couple of minutes for everybody to reset, stretch, get a quick trip to the washroom, water, whatever you need. So this is the fun lecture. This is where we get to talk about the passion of the research. Everything else I've shown, most of what I've shown you before is other people's works. I've snuck in a couple of the small stories from my group in the medchem realm. In this case, I've chosen to teach more about the synthetic chemistry and to think about chemical reactivity. And we might be able to relate some of the concepts here to the fundamental concepts we would have discussed in day 1. The perturbation of reactivity. So, I probably don't need to do a full introduction of my research group and my interests. We are organic chemists by training, organometallic chemists, natural product total synthesis chemists by training, but in initiating my career, I was really intrigued in fluorine chemistry, and so we predominantly focus most of our synthetic chemistry, medicinal chemistry, around this element. And it's a really interesting element for many reasons that I've described before. Maybe one other interesting fun fact, it's the only element that has a journal dedicated to it. So you have the Journal of Fluorine Chemistry. Other than maybe the Journal of Organic Chemistry, Organic chemistry is carbon chemistry, so maybe there's an argument there, but other elements don't get their own journal just for one element. So this has been a fun area. In terms of medicinal agents, you've seen over the course of the week that the physicochemical perturbations imparted by fluorine and fluorinated substructures influence the interactions between the chemical matter and the biological system. They perturb drug-like properties, and as a result, it's essential to prepare fluorinated molecules. You want to prepare them well, you want to prepare them efficiency, high yield, high selectivity. And so you need efficient strategies to be able to introduce fluorine exactly where you want in a molecule. There's a fundamental challenge, though. It's really tough to install fluorine in a controlled manner into your molecules. So classically, most of the reagents that are used are harsh, gaseous. They're toxic agents, things you don't want to breathe. You don't want to be in the same room. You can't do many of the classic reactions in an academic laboratory. You need to do it in an industrial setting. I'll show you some examples as we move forward. Fluorinated molecules also have distinct reactivities, so the electronegativity, the hyperconjugative effects. In many cases, those effects disfavor reactions that would normally work on non-fluorinated compounds, and when the reaction doesn't work, you need specialized solutions, specialized reagents, specialized catalyst systems, distinct reactivity patterns, distinct mechanisms to promote reactions that are going to be different than the standard organic chemistry that you learn, okay? In your coursework. Okay, so there are new rules, there are different sets of reagents, different specialized reactions. There are also innovative activations of alkenes or other functional groups that occur through fluorination, and so you get unique innovative reactivities that you can exploit, and hopefully those themes are evident in today's talk. So I'll go back to, I'll start the story back when I was a grad student. And when I was a grad student, I had an interest in organofluorine chemistry just as an intellectual inquiry. Okay, and so this was just a question in my head, like why do drug-like properties get perturbed the way they do? And that curiosity led to the writing of a proposal in grad school about how to prepare fluorinated compounds. And the starting point for that proposal was this thought right here. If you took a hydroxyl group, we can convert that hydroxyl group into a fluorinated compound. It's a deoxyfluorination reaction. At this point, there are dozens of reagents that will do this transformation. So I won't say it's a totally solved problem, but there are many solutions. Who knows which one might work for any given organic molecule. But if we take this deoxyfunctionalization concept and instead extrapolate it to other important fluorinated substructures, how would you accomplish this transformation? So this could be useful for a variety of applied chemists because you're taking these oxygen atoms that can serve as good proton donor or accepting groups, and you can do a lot of further transformation with the alcohols. Okay, they're feedstock chemicals. You find them in libraries. We know how to synthesize them. It's a great substrate to use for any transformation, these types of substrates. If we could convert those into fluoroalkyl groups in efficient, direct strategies, we would drastically perturb the properties of the molecules. And again, perhaps that's useful for a variety of applied industries. That was the general thought, and I wasn't sure how to do that, and I'll show you some of those solutions to that and how we've improved some of these processes over time. The group has generally explored deoxygenative strategies, decarboxylative strategies, or a subset of deoxygenative strategies, and then reactions of fluorinated alkenes. For purposes of today, I'm just going to talk about that first strategy. We're going to ignore quite a bit of work that we've done in the reactions of fluorinated alkenes. Now, the initial inquiry, the initial train of thought started with deoxytrifluoromethylation reactions, but I'm also going to demonstrate that with these strategies, we can make more and more and more fluoroalkyl groups that are important for my biomedical processes, and we've seen some of these over the course of the day. Some of these guys perturb basicity, benzylic positions, blocked. Okay, we talked about some of these substructures already and why they're relevant, so at this point, I'm going to not try to rationalize all the different substitutions that we're interested in, and this is just a subset. Okay, so the roadmap for the talk is here. In a 50-minute talk, I wouldn't maybe cover all of these, but in the case we have a little bit more time, I'm going to cover several different strategies that involve this deoxyfluoroalkylation strategy. a subset of strategies. There are several different catalyst systems here. You can see copper, palladium, you can see no catalyst system on the bottom. So we've taken this reaction pretty far, and hopefully I can tell a good story here. And I will tell a bit of the background in some of these reactions since I have a little bit of time, a little bit more of the thinking behind the scenes that went through, a little bit more of the problem solving. Some of that might be appreciated by the students. So I'll start back. This is Assistant Professor Day. Dr. Deepak was a postdoc at Kansas, and my group started doing that right there when he was a postdoc on about a mile away on a different side of campus. So in the literature, there is a solution to this deoxy-trifluoromethylation reaction. It requires a 4-step synthesis. In that 4-step synthesis, you first oxidize the alcohol to a ketone or aldehyde, use the Rupert-Prakash reagent to promote a 1,2 addition reaction and make a trifluoroethyl alcohol. This reagent, when combined with fluoride, will basically make CF3-, which can do 1,2 addition reactions. And that's how you get the alcohol. So it's just a 1,2 addition reaction of CF3- to a carbonyl. Subsequently, deoxygenation of the hydroxyl group is required, and there are multiple different ways you can do this. Functionalize the alcohol and do some type of reductive step. Okay, so there are multiple solutions for steps 3 and 4. Not necessarily a green process. Process chemists would hate this one, right? Workup, purification on every single step. Not necessarily green solvents in many cases. And you also have unnecessary redox steps. So we're taking an alcohol and oxidizing it just so that we can reduce it off later. Okay, it's a waste of steps if you can figure out how to more directly connect the oxygen to the trifluoromethane. Nonetheless, this strategy has been used to make quite a variety of biologically active molecules, fragments for drugs, biological probes in themselves. You can see nucleosides, amino acid derivatives, other small synthetic molecules that contain heterocycles, sugar mimetics. Like this type of strategy works in many cases. But certainly not green, not ideal, and the goal from the outset was to figure out a 1-step strategy to go from the alcohol or the ketone and get to the trifluoromethane. Very process type thinking, like process chem type thinking, but the inspiration comes from medicinal agents, and how could we improve the access to medicinal agents. So the initial strategy explored involves a decarboxylate of a reaction in which a halodifluoroacetate derivative decarboxylates in the presence of a copper-based salt and a metal fluoride under thermal conditions. The release of CO2 is an exothermic process. The process generates a metal halide salt. So if we start with the bromide of the chloride, that would generate a metal bromide or chloride salt as a stoichiometric byproduct that crashes out of the system. The copper CF3 is intrinsically nucleophilic and can do coupling chemistry with some type of electrophile. For purposes of the first part of the talk, we're talking about activated CSP2X electrophiles. Okay. Sorry, CSP3X electrophiles. Okay. So these are generally going to be benzyl, allyl, propargyl type substructures here. These are mild conditions you'll see for the decarboxylation. We minimize waste by doing this in 1 or 2 steps, and ultimately these are inexpensive reagents when you go look them up in any chemical catalog. The foundations for the reactivity I'm exploring come from Professor Chen's group at the Shanghai Institute of Organic Chemistry, who in a series of manuscripts nearly 30 years ago, over 30 years ago now, had reported this sequence in which the alcohol can get converted to the halodifluoroacetate ester. Isolate, purify, subject that to stoichiometric quantities of copper in addition to sometimes catalytic cadmium, which is a toxic additive. So it was a stoichiometric process that would occur, and we evaluated the mechanism by which he proposed this reaction occurs. I don't want to walk line by line through everything. I would like to highlight maybe 3 key points about that mechanism that really inspired a lot of the thinking behind the scenes. So initially the reaction started with copper iodide. The final step generated more copper iodide. So in principle, a catalytic process should be feasible in which we can reuse the copper. Pretty simple principles of catalysis here. In his reaction, the initial step of the reaction would generate, see the reaction of copper iodide plus your substrate generates an alkyl, benzyl, allyl iodide. And that would ultimately serve as the electrophile that undergoes trifluoromethylation at the end. So perhaps we need to modulate the concentration of iodide if we want to facilitate formation of this species. It turns out that that working hypothesis works in some cases, not others, on a substrate by substrate basis, and I'll explain that in a little bit. But again, it's something that was in the back of our minds certainly throughout the process. Finally, in Dr. Chen's reports, they estimated that the reaction would generate free difluorocarbene. That difluorocarbene could react with a metal fluoride salt, generate CF3-, which would ultimately give us the copper CF3. Now, in this process, the free difluorocarbene formed in the reaction could decompose many useful functional groups in molecules. And so if this mechanism is true, there's necessarily limitations in functional group compatibility. It'd be difficult to have alkenes, it'd be difficult to have acidic NH bonds and things like that. So if this is true, there are quite a few things that you cannot do with this difluorocarbene. I'll argue for a different mechanism. I'm going to argue for an intersphere decarboxylation for which there's no free difluorocarbene floating around in solution, and I'll show you that in just a little bit. So this is assistant professorhood. This is year one. Brett Ambler started this project, and ultimately other individuals continued over time. And further developed this project. But Brett really started this. He was one of my first graduate students. And over the series of a couple of years, he led a series of studies that did indeed accomplish catalytic processes. So in this case, we take the alcohol, the allylic alcohols, preform the halodifluoroacetate esters, and using copper-based catalyst systems, in this case using DMEDA, a ligand popularized by my PhD mentor, promoted the decarboxylative trifluoromethylation reaction. The benzylic substrates could also be converted. In this case, we don't use a nitrogen-based ligand. And in this case, we do add extra Ki. And so that's what I was saying. Some of these substrates benefit from the addition of more and more and more Ki. And that certainly was true for the benzylic substrate. And finally, the propargyl substrates could react with distinct ligands, DMEDA or 1,10-phenanthroline, to generate either propargyl or allynyl products in a ligand-dependent fashion. And the ability to control the regioselectivity of the transformations by the ligands was a key feature of this chemistry. Okay. So that's older chemistry. It's published. The combined series of reactions that occur under reasonably similar conditions tolerate a wide variety of functional groups. You can have O, N, S in your substructures. You can have halides and pseudo-halides built into your substructures. A variety of heterocycles are tolerated, nitro groups, alkene groups that can undergo further functionalization. Importantly, the reaction actually tolerates a variety of ketones and esters and aldehydes and acidic NH protons. And the compatibility of those substrates suggests that, number one, you don't have free CF3- in the reaction. The decarboxylation and the formation of the copper CF3 must occur within the solvent sphere of the metal. Otherwise, these functional groups would react with CF3- and additionally with difluorocarbene. So maybe I'll go back one more step. Difluorocarbene can react with acidic NH bonds. It can react with alkenes. So it's arguing for a distinct mechanism for decarboxylation and formation of the copper CF3 species. There were still some limitations, some things that don't work, basic alkylamines, pyridines, quinolines. That was something that we've been working on for some time, and we partially solved that. Now, if you're looking at the value of these products for medicinal chemistry, an analysis some years ago indicated there were tens of thousands of compounds reported in patents that would have these trifluoroethyl substructures that you see here. So others in the field, in the medicinal chemistry field, were trying to make these for various reasons. So it seems like a reasonable target to try to improve, to which we can improve the access. Additionally, the trifluoromethyl allyl substructures can be further functionalized by either oxidation chemistry or reduction chemistry to make simple fragments that could be elaborated into more complex biomedically relevant substructures. Okay. So these are reasonable enough fragments. Again, we can improve the preparation of those. Somebody else can use them in their medicinal chemistry campaigns. We are happy with that. The allynyl products that would be formed from the propargyl substrates could be further functionalized to generate a variety of carbon-nitrogen, carbon-carbon, carbon-oxygen, and carbon-boron bonds with exclusive regiochemistry. So these are chemoselective processes. You have two alkenes There's 3 different positions here that you could maybe form that carbon-boron bond, right? You could form it here or there or there. In every case, we exclusively get formation of whatever bond we form. We get it exclusively at one position. Now, there are different mechanisms for these, so we can't like walk through every single example here, but this was an attempt to demonstrate that you could access nice fragments from this type of a trifluoromethylalene substructure. Mechanistically, this reaction occurs by a process that we proposed looks something like this. At the start of the reaction, we have a copper halide ligated by some type of nitrogen-based ligand in 2 of those 3 systems. There's an initial activation step in which the copper iodide reacts with the halodifluoroacetate and KF before the catalytic cycle initiates to generate the copper CF3. So when we run these reactions, many times we mix this combination together first, about 10 minutes, 15 minutes, a little bit of heat, maybe 50 degrees, maybe 80 degrees, based on which system we're dealing with. That generates the copper CF3, then you put in the substrate and start the reaction. Okay? So we do that sometimes. We do it for the allyl system, we do it for the propargyl system. It doesn't benefit the benzyl position. From there, our copper CF3 is the nucleophilic species that can react with an electrophile, and there are various different electrophiles that seem to vary according to the structure of the R group. So in the case of the allylic electrophile, we can actually run the reaction in the absence of iodide. So we can start with a copper PF6 or copper BF4, no iodide at all, and those reactions perform just fine. So we think that's a system for which we don't go through an iodide intermediate. In contrast, for the benzyl electrophiles, we add excess iodide, and we can track by GC the buildup of iodide over the course of the reaction. The highest concentration of iodide simultaneously occurs at the maximum rate of the reaction, and then as that concentration falls off, you also see the overall rate of the reaction similarly fall off. So evidence that that benzyl iodide is a key intermediate. So in the benzyl case, we think it's the iodide. In the propargyl case, we speculate that the electrophile, which is initially that bromodifluoroacetate, converts to a bromide, and we've done stoichiometric studies pushing material forward one step at a time, one step at a time, one step at a time to demonstrate that progress. Okay. So the propargyl likely go through the bromide. Now, after the substitution process, we ultimately get back to a copper difluorobromocarboxylate species, and this does an intersphere decarboxylation. It generates a copper carbene species. That copper carbene is intrinsically electrophilic at this position, so fluoride can add into this position and get you back to your initial copper CF3. Okay, so it's an electrophilic carbene at C for this case. You have Fischer carbenes and Schrock carbenes. This is a Fischer carbene. So that's the intersphere decarboxylation. This is how we rationalize not having free CF3 minus or difluorocarbene floating around in solution. So that's great, that's wonderful. That is a series of publications to get your career started. That we didn't hit our goal. The initial goal was to get a one-step process. And this required 2 steps, so we have some inefficiency in atom economy and step economy there. You have to isolate, purify this material, run a column. Some of them are a little bit unstable, and so certain functional groups on the molecule are incompatible, and so we needed a better solution to this problem. Now, remember our initial goal. We want to take the alcohol and go straight to the CF3, so here's an early experiment. This is like when I was in lab and running reactions myself. So this is my experiment, like one of the few experiments that I actually ran in this slide deck. You can take some of these activated alcohols, in this case you can see the series here, and subject them to either the metal halide salt or the ester and promote the decarboxylation. And the yields on the bottom are not particularly ideal, but they do demonstrate catalytic turnover. And proof of concept in like year 2 of your career, that's a pretty good result. So we have 10% copper iodide, 30 to 40% yield. This combined 40% yield in one reaction that is still promising, and we can further develop that chemistry. So to develop this chemistry, we're ultimately going to try to make a new reagent. I'll tell you a little bit about the design of that reagent. The working hypothesis at this point is that the alcohol would undergo a transesterification or a condensation reaction, depending on which precursor you used here, to generate the halodifluoroacetate ester in situ. And then the copper-based catalyst system would promote the decarboxylated trifluoromethylation. Now, the problem with this proposed sequence is that the initial transesterification or condensation would generate a stoichiometric quantity of water, methanol, or some hydroxide, and maybe that was problematic. So you can run a quick experiment to test that. Take your substrate, throw in any of those potential stoichiometric byproducts and see if they antagonize the reaction. So on this day with no additive, the parent reaction gives an 80% yield. You can see in the presence of one equivalent of methanol or ethanol, you see that yield drop off. So we know this is a challenge, this is a problem, and now we need to solve that problem. We need to figure out how to generate a reagent for which the stoichiometric byproduct does not antagonize the reaction. So you can go about this problem several ways. You could have a grad student just go start making everything they can possibly think of, prepare it, try it, prepare it, try it, prepare it, try it, hopefully you get the right answer. We chose a different approach. In this case, we chose to get a bunch of these leaving groups and run the same reaction. Take our substrate, run the reaction with a bunch of these and see what does not antagonize the reaction. Then we can prepare a smaller subset of proposed new reagents. So that's the experiment I'm showing you here. The conditions, you can see similar conditions to what you've seen the entire time. Is the allylic substrate. We'll look at a variety of leaving groups, potential leaving groups, and see if they interfere with the process. In this case, your yield was 75%, not 85% for the day we ran this reaction. A variety of alcohols were explored. You can see trifluoroethanol was all right. It did not antagonize as much as others. A variety of phenols were explored, and perhaps some of those might be useful as leaving groups in this process. Thiols, you can see other nitrogen-based heterocycles. There's precedent literature for many of these serving as substrates for transesterification reactions. And so there was sufficient evidence in the literature maybe these might work. Ultimately, some of the ones that we probed and explored are highlighted in red, and then we need to go back and synthesize the comparable reagents and test them in reactions. So there were issues with a couple of them in terms of stability, hydrolytic stability, stability on silica, and ultimately we came to this phenyl bromodifluoroacetate ester as being the key reagent. So this reagent promotes the transesterification reaction. That transesterification reaction under our reaction conditions is promoted by the KF that's in solution. So stoichiometric studies, just looking to see what forms the ester, KF actually does. It's not copper, it's not just thermal, it's not other additives. The KF actually promotes the transesterification, and then we have this substrate prepared to generate to serve as the substrate for the copper-based catalyst system. The reaction works for a variety of substructures. Again, we're going from alcohol to CF3. These are one-step reactions. These are not the four-step sequences that had been used previously and I mentioned earlier on. So the yields are good enough. You can do some of the allyl substructures, benzyl and heterobenzyl substructures. The reaction of propargyl groups still gives those allenes with the right catalyst system. Okay. So I don't want to go through too many examples or highlight much here. I want to keep moving on, talk more about the science and how it might impact some preparation of target molecules. So this is an example that comes out of the literature of a group trying to make an agricultural chemical. They take the heterobenzyl substrate, convert it over to the heterobenzyl CF3 in 4 steps and 30% yield. Again, that sequence involves oxidation, 1,2 addition to generate the trifluoroethyl alcohol, and then 2 steps to reduce off that alcohol, this time using stoichiometric tin. You also have to use stoichiometric manganese early on. Okay. Using the first reaction sequence I mentioned before, you can generate the ester, isolate it, purify it, and then subject it to the copper-based catalyst system and deliver the same product in half the number of steps and double the yield. Alternatively, you can take the reagent I just showed you, do it 1 step, almost double the yield. Okay? Certainly saving steps and more economical for principles of green chemistry. Okay? So that's how it might apply to some campaigns. This was not the final target molecule. There's further functionalization of the furan that was done by the other group to make other compounds. Okay. So that brings us up to 2019, and there's another, nope, this was it, these two papers in 2019, and then what happens in the world? COVID, right? And everything shuts down. People can't go to college, can't go to work, can't go to the lab to run experiments, and so what do? We sit and we start reading, we start problem solving and doing what we can do on paper, and that's where the next project emerged. This next project emerged because we couldn't do anything for it, and we had to go back and think about new challenges and new problems and new solutions. So sometimes taking the time to stop and think and just, it's good. Okay, dig back into some literature, look back at your old notebooks, and that's exactly what happened. I'll give you a little bit more information on this. So this story actually goes back to a GRC conference in the US, 2018 notebook, and I had this written down. I really did have 3 question marks over this transformation. I was just sitting in the audience watching somebody else give a talk, and I was like, I got curious about how do you do this? There isn't a solution to this. We had a little bit of experience with this type of transformation. It's a 3-step process to do it in principle. This was that FDA-approved therapeutic I mentioned at some point during the course. That's an antitussive. The synthesis, the preparation requires taking the compound has the methyl and the methoxy group and protecting the nitrogen as this carbamate, demethylating over here, and then it's a 3-step sequence to convert the phenol to the boron using the triplet anhydride and pyridine, and then a meioborylation, and then you use the Hartwig trifluoromethylator reagent. That's a stoichiometric reagent for doing aromatic substitution reactions, and we got the CF3 there. Okay, 3 steps, 30% yield, not ideal, but good enough for medicinal purposes. Okay, so we need to improve that process, and again, COVID allowed us to do that. Now, to be competitive in this field, you have to have an awareness of other ways of preparing these aryl trifluoromethanes. And so I've summarized some of the most impactful methods here on this slide. The first 2 require harsh reagents, oxidizing reagents, and or gaseous reagents that preclude the presence of sensitive functional groups and are difficult to run because, like HF and SF4, like, you don't want to be using those in simple academic labs. If you're going to make an impact with those, you're going to be in an industrial setting. Specialized reactors, they decompose a lot of stainless steel and other things. Like, you need specialty precautions and especially systems to be able to do these types of transformations. Radical functionalization typically occurs with poor regioselectivity, so we want to do one CH bond and not the others. That's a challenge. And finally, the metal-catalyzed cross-coupling reactions, number 1, are not the most effective right now. And number 2, if you have highly substituted derivatives, the preparation of the substrate itself might be tricky. So these methods generally fail when you have highly substituted target molecules. So if you have molecules for which you have many different CH bonds in the molecule, it's difficult to see why you would functionalize one position as opposed to the others. In some cases, preparation of the halide or carboxylic acid precursor might be a challenge in its own right. And with some of these other reagents, you can't have certain sensitive functional groups. If you have maybe 2 methyl groups next to each other, how are you going to selectively functionalize one and not the other? Okay, so a lot of challenges here if you had molecules of more and more and more complexity. Even though these are flat planar rings, they're still tricky to make currently. So there were several different mechanisms, and this is probably over the course of a month where we're going back to the books and the drawing board and planning different sequences. And here's one sequence that stood out. And so if you consider a reduction of a phenol with a metal-based catalyst system, that would generate an enone. In a subsequent step, use the Rupert-Prakash reagent would generate the trifluoroethyl alcohol, and then we need to do an elimination and oxidation to get back up to the arene. So that was the working sequence. There are some catalyst systems to do this. There's really no minimal precedent for doing this, and definitely not with a CF3 group on it. And I'll mention later on why that CF3 group is pretty substantial and important. the next day, a couple days later, there was a realization that there's actually a really powerful transformation embedded within this figure. If you only focus on this second part, that would be really useful, because the enones themselves are very versatile substrates. You can functionalize those with all kinds of reactions. You have the alpha position, either one of them, beta position, you can do gamma functionalization. Maybe we can dial in substituents in a controlled fashion, really control their installation in terms of the regiochemistry, and with a wide variety of decades and decades and decades worth of transformations of these enones. Maybe we could be pretty creative and access compounds of more and more complexity if we can figure out how to promote the deoxyfluoroalkylation aromatization sequence. So this is where the innovation really is, connecting these two groups. Now, the work was done predominantly by Pankaj, a former student. He's doing a postdoc right now. Other individuals helped quite a bit over this project and are following up on some of Pankaj's additional leads that he left behind. But he did most of the work that you're going to see on the rest of the next 3 papers. So the solution, this slide is probably a year and a half of graduate work on one slide, and that's sometimes the way it goes. Okay. He developed 3 different solutions at the outset to this problem, and you'll understand in just a minute why we have 3 solutions for an initial attempt. The solution, the first solution, involved the use of the Rupert-Prakash reagent to do a 1,2 addition reaction that generates a mixture of alcohol and silyl ethers, and you have both cis and trans isomers when you consider the oxygen to base group relative to that phenyl group. We did characterize all those and figure out what was going on there. You don't need to separate them. In the exact same pot with no purification, no workup, no anything, you can toss in PTSA, DDQ, heat the reaction mixture, and you get aromatization. Now, DDQ has 2 different mechanisms by which it can operate. It can operate by a mechanism that does hydride abstraction. If you abstract hydride from your substrate, you would get some type of a cation intermediate. It can also do H-atom abstraction. If you abstract an H-atom, you would get a neutral radical intermediate. Now, it turns out the initial substrate we were using was distinctly chosen because it's going to be easier to oxidize. It has a benzylic position that can stabilize these types of intermediates. So when you're starting a new reaction for methodology, pick something that's easy, that's going to be likely to give you success, and then move to harder problems. And that's what we did here. If the substrate does not have a stabilizing group, in this case the T-butyl substrate, the 1,2 addition reaction works just fine, but the oxidation reaction no longer works. 0% yield, that's also 0% conversion. We can re-isolate the material shown here. We do a little bit aqueous workup so we get all of the alcohol. You can re-isolate that. Okay? And again, that substrate does not benefit from an activated benzylic position. It's tertiary, it's pretty good for some mechanisms, but it doesn't work in this case. To demonstrate that the CF3 is really disfavoring the reaction, I like to show this example from C.J. Lee's group at McGill University. In their reaction, the 1,2 addition reaction of a Grignard reagent makes a comparable intermediate. The elimination and subsequent oxidation with DDQ occur under mild conditions. The CF3 is resisting oxidation. This occurs easily at 50 degrees Celsius. This reaction, I'll show you, goes through a similar vinyl intermediate, but we require 150 degrees to do this because of that CF3. So, how are we going to solve this problem? Well, there were quite a few different attempts at solving this problem and promoting the reaction. Ultimately, Pankaj found that you can do the 1,2 addition reaction, force elimination with SOCl2 pyridine, and then run the material through a silica filter that generates a semi-pure form of the vinyl trifluoromethane, and then we can use a combination of AIBN and NBS to promote the oxidation through radical intermediates. So there are no cationic intermediates in this sequence here. That works for both the unactivated and activated substrates reasonably well. If you have the activated substrate, you can go ahead and take the vinyl intermediate also subjected to PDSA DDQ and promote the oxidation. So you have 3 different sets of conditions. If you have different substrates, you get a different attempt. And we know that for any individual reaction we try to run, many times you need multiple sets of conditions. How many amide bond forming reactions do we have? How many different reactions to go from alcohol to an aldehyde do we have, right? Plenty of different sets of reactions. For any individual transformation, it's okay to have multiple solutions that you can turn to for different substrates. So the reaction works for a variety of substructures, some of which are shown here. Nitro and cyano groups, electron deficient. You can use halides that can be further functionalized by a wide variety of cross-coupling reactions. Donating groups are tolerated, amines, ethers. You can see aliphatic systems. If you have groups, I'm talking about these. If you have groups that have acid-sensitive substructures on them, you can get them to work. You just have to remove the acid and lower the temperature. I'll show you a little bit more data on that in just one slide. And orthosubstitution is tolerated. Many times orthosubstitution will be difficult with transition metal-based coupling reactions, and we can do it here reasonably well enough. In addition, I like this example because if you had radical functionalization chemistry, and if you had a CH here, you'd never functionalize that position with a radical. It's too sterically hindered for the radical to attack there. If you try to use like the Schwartz method, where you have a methyl group and you trichlorinate it and dechlorofluorinate it, there's no way you're going to hit this methyl group as opposed to the other 2 selectively. So there'd be some challenges there. So here's an example of a vinyl ether here. Vinyl ethers hydrolyze under acidic conditions. That's been known since the 40s or 50s. That's an old reaction. In this case, the conditions, the oxidation conditions that use PSA DDQ give you a mixture of the phenol and the ethers. If you remove the PTSA and heat the reaction a little bit less, you can improve the yield and improve selectivity for formation of the ether product. Similar story is true for products bearing an ester. TMSCF3 is strongly nucleophilic and will react with most esters. So to disfavor the reaction of TMSCF3 with the ester, you need to use a bulky ester, and that's why I have the T-butyl group on there. The problem is that the T-butyl group comes off with acid. So there's a chemical incompatibility there. If you do the oxidation under the initial conditions, you form the carboxylic acid. Great yield if you want to make a carboxylic acid, but if you want the ester retained, that's not the way to do it. So if you remove the PTSA, use a less forcing temperature, you can invert the selectivity, generate the ester. We do have a next generation set of conditions that improves that yield and selectivity even further. Okay, so we're still working with that. So the strategy itself enables access to a wide variety. So a wide variety of products. In this case, I'm highlighting that you can take commercially available simple materials and in a single step access comparable trifluoromethanes. And if you try to use other methods, the precursors don't work. You need a de novo synthesis, like that. You have to figure out a new synthesis of it. In some cases, they're pretty expensive. This is a reasonably expensive chemical when you look at that price, but there are chemicals of comparable complexity that you can convert over to the trifluoromethanes. So again, we just want to think about other starting points that are orthogonal to things that might be unavailable or ridiculously expensive. Using routine synthetic organic logic that you have been introduced to since your sophomore organic year of chemistry, you can access all kinds of substructures. So I'm just going to show a series of short syntheses that can convert a simple starting material into a variety of products. We can use a simple bromination reaction, generate a vinyl bromide and convert that over in a short synthetic sequence. That bromide enables functionalization by a wide variety of cross-coupling reactions, one of which we can show there. There's the Ho-Suzuki reaction. That product might also be accessed by doing the Suzuki reaction first and then the deoxyfunctionalization trifluoromethylation reaction. That gets you the same product. If you want a functional handle here at this position to do further chemistry, you can introduce the halide in that step. here NCS to introduce the halide, then we convert that over to the final product in reasonable enough yield. If instead we want to invert the halogen and carbon-based substituents, we can do that, but we need a new synthesis. In this case, we can go back. There's an activated methylene here at this position, and we can do a functionalization there with our carbon-based reagent first. Then we do the halogenation. We've inverted the carbon and halogen-based substituents there, and then we can convert that substrate, that enone, over to the aryl trifluoromethane in the next step. Lots of opportunities. Sorry, I'm talking so much. It's fine. You can't do notes after all this time. Okay. So there are many opportunities to use routine synthetic organic logic to build substrates and convert them over. Okay, so that's what I've tried to highlight initially. You can also generate these enones by a wide variety of other strategies. There's reductive conditions for getting into the substructure. You can do other annulation reactions to introduce the enone substructure with high complexity. I'll just show a couple of examples real quick. Here we have a metal-based coupling reaction that couples two simple building blocks to make a tri-substituted enone, which ultimately gets converted into a tetrasubstituted arene. Other annulation reactions can also be used. In this case, it's a net 5+1 cycloaddition reaction to snap in this C1 unit bearing a quinoline moiety. This ultimately converts over in reasonable yield. Palladium-based catalyst systems, and some other transition metals don't like pyridine like nitrogen atoms, and so many times this type of substructure might be problematic for some other systems. Natural products might also have enones and ketones, cyclohexanones, built in them, and so those can serve as substrates themselves for further functionalization prior to aromatization. So here we do a 1,4 addition reaction, introduce a new substrate, and then convert it over with the initial set of conditions. And so there's no shortage of creative things you could do to take enones, prepare enones, highly substituted enones, and convert them over. Okay? So that's the moral of the story here. At this point, we focused on the CF3 group. There are many other useful fluorinated functional groups that one might want to introduce into your molecules, and the method can also be applied for other fluorinated functional groups. So here's a slide in which we will look at the 1,2 addition reactions of different fluorinated functional groups, and we'll use one of the sets of conditions before two different sets of conditions here to promote the aromatization. A variety of fluorocarbons are readily added in. In some cases, we use a silyl protecting group and a metal fluoride to generate the effective anion. In other cases, the higher molecular weight fluorocarbons, you can get away with the iodide precursor and use a lithium halogen exchange to generate the nucleophile. Those oxidize in the presence of PTSA-DDQ. If you have other heteroatoms in your nucleophile, such as oxygen, so this would be a ketone, this would be an ester, this would be a sulfone, those fluorophosphonates, like that was the very last slide before we broke for lunch. Okay, you can do 1,2 addition reactions with those. You just need different strategies for generating the nucleophile. They do the 1,2 addition reaction just fine. And then the aromatization requires the SOCl2 pyridine conditions. Okay, so you can do all kinds of things with that. Heterocycles are tolerated, very important for pharmaceutically active agents. Electron-rich heterocycles, carbazoles, indoles, thiophene are tolerated. Imidazoles, electron-rich, electron-deficient pyridine-like systems are tolerated. This slide demonstrates that you can have the heterocycle tethered to the ring that is formed, or it can be benzanulated. Okay. What about rings in which your heterocycle is attached, or part of the CF3 is attached to the heterocycle that you form, right? I haven't shown that yet. So the proposed sequence is here. The proposed sequence would require a substrate that looks something like this. You do a 1,2 addition reaction with TMS-CF3, eliminate, and then we need to do an oxidation here. The challenge is there's an incompatibility with TMS-CF3. TMS-CF3 reversibly forms difluorocarbene, and the difluorocarbene will react with NH bonds. It makes the NCF2H. So we need a protecting group. But if we choose strategically a protecting group, perhaps it might undergo an elimination reaction and generate one of the unsaturations, and then we're just one unsaturation away from the final product. Okay? And this should be an easy step because that's the step that forms the aromatic ring. So that should proceed presumably under more mild conditions. So hopefully you're thinking a little bit about like what group I would put on there. Ultimately we went with a sulfone. If you have an SO2 pH, this is a sulfonamide group. That sulfonamide group might leave with either strong bases that can deprotonate and promote the elimination loss of SO2 minus. Alternatively, under radical conditions, you can do H atom abstraction and then a radical elimination of phenyl SO2 dot. Okay, so you have multiple different opportunities for success with that protecting group, and that's why we chose it. We can try a whole bunch of different conditions to promote the elimination. Ultimately, what works, you do the 1,2 addition reaction, as you've seen many times, elimination to generate the vinyl CF3. We do have a quick silica filter here to clean out some of the junk, and then just simple DDQ does it. Temperature a little bit more mild than some of the other systems. Okay. So I'm going to pause there on just methodology. There are many, many, many different opportunities to use this strategy. I mean, it's not just a reaction, I think it's a strategy. And then you can make all kinds of different molecules with that. A theme from the course involved thinking about reactive intermediates and how fluorination perturbs the reactivity of molecules. Previously, we were thinking about reactions that occur in biological settings, but let's pivot now and just talk about the organic chemistry and how the fluorine perturbs the reactivity of the oxidation sequence. Okay. So this is similar to one of the slides I gave in problem set, and we talked through it once for those of you in the class, but maybe it'll make more sense now that you've seen the preamble, the rest of the papers before it. The key data shown here summarizes the different temperatures that are required for oxidation of these different substrates. So we have the example from C.J. Lee, that's a styrene, the trifluoromethyl vinyl substructure that has a stabilizing group and the one that has a non-stabilizing group. Low temp, good yield. High temp, good yield. That thing doesn't like to, it laughs at you when you say, I'm going to oxidize you with DDQ. Okay, doesn't do anything. So to estimate how these reactions are proceeding, Pankaj ran a series of calculations, initially doing hydride ion abstraction, calculating hydride ion affinities. And so these are calculations in which we systematically remove H minus from the various positions and calculate the energy associated with H minus and the carbocation. Okay. And we focus on 3 different positions, the 2 allylic positions and then the position here that's attached to the group shown in blue there. For the model systems, we have 6 systems here that we'll look at initially for this slide. You have a styrene with the stabilizing group, a styrene without a stabilizing group. You have just a simple methyl group. We didn't study this experimentally, but it's an important benchmark to compare to the CF3 group. Okay, so it demonstrates, how difficult is it to oxidize this type of a substructure to make a toluene relative to a trifluorotoluene. So that's a control substrate. Just to calibrate everybody, with the easiest example you have here, the hydride ion affinities are reasonably low in all cases. You can see the weakest CH bond here. If you make cation there, it's allylic, but when you put the cation here, you also have benzylic stabilization, so you have a nice extended conjugated system. The next substructure over also has a reasonably, it forms a reasonably stable cation over here, and that stable cation also would extend and resonate all the way through the system there. I hope it's not dying in battery. You see it jittering a little bit more, and that's not me, it's jittering on its own. So we'll try resetting it. Note there are other weak CH bonds in the molecule, but we don't need more, like any of these are good enough options. We'll go over and look at the next pair. The next pair has the methyl group here. The allylic position is still reasonably weak. as is the benzylic position. So there are multiple opportunities to abstract H minus, generate a stable carbocation, and then continue the sequence. And the same thing is true for the next example down. You still have a weak allylic CH bond here. This one's tertiary, this one's still allylic, but there are still a couple of reasonable options there to initiate the sequence. In contrast, when you get to the CF3, you get significant perturbations to both allylic positions. So look at those hydride ion affinities. You're upwards at near 250 kcal per mole and 245 down here on the lower case. Those are too much. Like they're too hard to rip off those hydrides at those positions. Now the difference between the substrates is right here. It's the benzylic position relative to just the regular tertiary position. This is still weak enough that you can oxidize it under high temperature, but this one's just too high, and it resists the hydride abstraction at that position. That's how we walk through and rationalize the oxidation data that we see here on top. Okay, so summarize that there. Low HIAs, low temperature, higher HIAs, and then this one doesn't do anything at all. Okay. What's going on? Okay, there we go. So there are other mechanisms by which one can oxidize a substrate, and perhaps you could do one electron oxidation. There are some oxidation reactions that we're aware of in the literature that involve some type of strong oxidant ripping an electron out of the substrate. I'll just show you a series of model substrates and then this one up here, and these are calculated one electron oxidation potentials. You can see for the styrenal system, 1.4 volts. We have a methyl group here, a little bit higher in energy, 1.6 volts. You put the CF3 group on there, and you're upwards of 2.5 volts, so certainly resisting oxidation. If we think about any mechanism that involves single electron oxidation of any of the moieties on the molecule. So that's not going to work. Pankaj did make some attempts in this space, but ultimately we found an alternate strategy that involves H-atom abstraction. So by H-atom abstraction, you're going to go through the neutral intermediates. Okay. So we might look at the substrate and identify the weak CH bonds. You have C3, C6, and then C4. Abstraction of any of those hydrogens would give you radicals. Just for purposes of the discussion, we're again going to just look at a smaller subset of molecules, not all the phenyl substituted ones, just the T-butyl substituted ones that were previously resistant. The bond dissociation energies at C3 are reasonably low regardless of the substitution. Phenyl, H, CF3, all of them have weak enough bond dissociation energies to rip off with an appropriate reagent. Okay. At the other position, the C6 position, you also have reasonably weak CH bonds there. So you have opportunities to initiate radical oxidations that involve an initial HAT step using this type of strategy. Ultimately, what works, remember, NBS, AIBN is going to be the series of reagents that we use to promote this. Again, we think it's going through these types of radical intermediates. Okay. And we do have some experimental evidence. Takeaway messages: if you're trying to go through cationic intermediates and you have your CF3 in the molecule, that's tough. Okay, you're facing an uphill challenge. If you're exploiting a moiety that can stabilize the cationic intermediate, you have a chance. But instead, if you turn to neutral intermediates, you have an even better chance of getting these oxidations to occur. So the CF3 group is really powerfully changing the mechanisms that we have to use to promote this oxidation. Okay. So, ongoing, what are we doing in this space? We are developing next generation systems for this transformation. We have things already. They're working down below 50 degrees based on some of the learnings and application of other cool, innovative chemistry behind the scenes. So look out at that for the future. And we're also always thinking about other fluorinated functional groups that we can use. So that kind of concludes where I wanted to be at the end of the first part. And I think we started like at 2:15 or so. So I'm like 55 minutes, pretty close to where we wanted to be. How long of a break do we want to take before we move on to the next sequence?
5 minutes. It can be quick.
5 minutes?
Short break.
Yeah. Okay. We'll take 5 minutes and be back.
So this is not related to drug or anything, but to
All kinds of other before. The longest we've gone, I think, is C6 F13. Peripheral isopropyl typical range there. I don't have any personal interest in going further. Maybe you could do some, you can search. Yeah, right. There's some other Sorry?
Okay, we're back. Those were kind of loud, a little bit of feedback. So, when we left, we were doing a lot of fluoralkylation chemistry. And fluoralkylation, it's certainly important. I'm going to pivot and move on to some other chemistry, and this other chemistry comes from the phase in the group after we had established that the copper chemistry, and after that was already in full speed. Again, there was an interest in exploiting these strategies to access a wide variety of fluorinated substructures, and in early attempts to extrapolate the decarboxylative coupling chemistry to the preparation of fluorinated ketones. We saw how cool those substructures are earlier today. So in an attempt to get the copper chemistry working on to make these types of products, we ultimately were unsuccessful and pivoted to palladium catalyzed coupling reactions. So a segment of the talk, the rest of the talk, is going to involve palladium. Fluorinated ketones, I summarized the importance already. This is the exact same slide that you saw 3 or so hours ago. They have unique properties, and they can be used for a wide variety of targets. The proteases are great. You have great conformational control. On the other slide earlier, this was acyclic, and now it's cyclized, and I mentioned that verbally, but now you can see the substructure there. A whole bunch of other targets can be modulated with these types of molecules. As synthetic chemists, we are trained from our first synthesis course that when presented with a fluorinated ketone, we always consider disconnection of the C-alpha C-beta bond. Now, ultimately, there are other bond constructions that you can use, but as a synthetic chemist, that's a retrosynthetic disconnection that should be automatic. So, in the forward reaction, you need some type of a nucleophilic enolate that's intrinsically delta minus at this position to attack an electrophile. We're thinking about simple reactivity right now, SN1, SN2 type processes. I've highlighted the challenges already with this type of bond disconnection. You just didn't realize what I was setting you all up for. Okay. So again, another slide I showed on the conformational control problems, right, the tutorial there. If you attempt to deprotonate this type of a fluoromethyl ketone, when there are other CH bonds available, here we have 2 alpha CH bonds, the non-fluorinated position, using either strong bases or weak bases, the reactions deprotonate at the non-fluorinated position. You do not form the difluorinated enolate that's essential for the bond construction that's shown here. Now, to solve that problem, there are other strategies. You could make the same enolates using a bromo difluoroenolate, for example, or other halide at this position, using reducing metals, for example, zinc, to make a Refermatsky-like reagent. You can generate the appropriate enolates. There's also some retroclason chemistry that's out there that also would do a C-C bond scission reaction to generate the same enolates, and then you can attempt the alkylation chemistry, okay? So deprotonation is tough, but there are some other strategies out there that you can use. The second fundamental problem with this disconnection is that the fluorine atoms decrease the nucleophilicity of the alpha position. They decrease the nucleophilicity through a sigma withdrawing effect, and it's sufficiently decreased such that simple electrophiles preferably react at the oxygen, not at the carbon. So you get this methyl ether as opposed to making the new C-C bond here at the alpha position. Okay? So again, another fluorine effect perturbing the reactivity. It's perturbing the deprotonation, and it's perturbing the C-C bond forming reaction that we want to happen. There are some recent solutions to this challenge, this problem. An older solution would involve the use of superstoichiometric zinc. A newer solution after, 5 years after we were in this space, involves the use of HFIP as a unique solvent. We've seen HFIP in some other cases the last couple of days be a really important, yesterday actually, right? A really important solvent for promoting some of the asymmetric transformations, the phosphine catalyzed reactions. So anyways, you can use some additives, you can make the C-C bond that you want there. That's great. That wasn't available at the time. We resorted to a different strategy in which we need to set up our substrates a certain way. So in this case, we'll take our electrophile and attach it to the nucleophile using CO2 as the linker. And with this strategy of palladium catalyzed oxidative addition to the benzylic position and subsequent loss of CO2 places the palladium at the appropriate fluorinated position. There's no isomerization over to the non-fluorinated position. So it's a decarboxylated strategy for generating the appropriate enolate, and then from this enolate, palladium-2 to palladium-0 reductive elimination would generate the C-C bond. So that's how we solved those two issues, those two problems using a palladium-based catalyst system. The system itself works for a variety of ketones. You can see heterocycles are tolerated on either the benzylic moiety or over on the other side, the ketone. Electron-rich and deficient substructures worked. These are done at 120 degrees. We require 140 degrees for this reaction because you have this alkyl tail. The alkyls are a little bit more difficult to work with, and you need a higher temperature for that. The strategy also works for the preparation of allylic substructures, and so the key disconnection is shown here. We can break the C-alpha, C-beta bond. When we break that, we have a difluorinated enolate. And this one is showing the anionic charge on the carbon as opposed to oxygen, but you have the different resonance forms of that hopefully is easy enough to see. And we would have an allyl cation. We link those two species with CO2 when we're preparing the substrates. In a long history of palladium catalyzed cross-coupling reactions, allylation reactions of hard nucleophiles, ketone enolates are hard nucleophiles, there's a wealth of literature indicating that hard nucleophiles preferentially react at the terminal position to make these linear products. Hard nucleophiles rarely will attack at the internal position to make these branched products. Okay? There are a couple of rare cases. One of that was available when we started the project. This one came out kind of after we had our first publication in this area. Okay. But with palladium catalyzed systems, hard nucleophiles react over there. It turns out that fluorine perturbs the reactivity, so we can access either the linear or the branch products as a function of the ligand we use for the system. So if we have different phosphine-based ligands, you can select one product over the other. A series of ligands is shown here, demonstrating the structure-function relationships of the ligands. If you have a bulky biaryl monophosphine, here's the T-butyl group, you predominantly form the linear product and good selectivity. As the phosphine becomes less bulky, the selectivity flips. And if you make it electron deficient and smaller, you get even better selectivity. Okay, so the substituent of the phosphine regulates the selectivity of this transformation. I'll explain why, or a working model, in just a couple of slides. The reaction works for a variety of substructures shown here. Again, T-butyl Brett-phos generates the linear product, phenyl X-phos generates the branch product. In the case of the branch product, the selectivities are excellent, regardless of the substituents on the ring. So you have electron-deficient substrates, electron-rich substrates, awesome selectivity. Most cases are greater than 49:1. However, the selectivity varies as a function of the groups on there for the linear cases with T-butyl Brett-phos, and I'll explain why that's important in just a couple of slides. Okay. The ability to access the branch product is dependent on the fluorination state of the substrate. So in this series, I'll just show two reactions for the difluorinated, monofluorinated, and non-fluorinated substrates. And we're going to look at the two catalyst systems, the catalyst system that predominantly forms the linear product and the catalyst system that forms the branch product there. All systems can produce the linear product. That's the product that's typically easier to produce with palladium-based catalyst systems and hard enolate nucleophiles. Excellent selectivity with the difluorinated, the non-fluorinated, and the monofluorinated. This reaction itself with the monofluorinated had been optimized by others, so we spent no time trying to improve this reaction. There are other systems that can do this just fine. Palladium can do that. In contrast, only the difluorinated substrate can access the branch product. And you can see the optimized conditions there, excellent yield, excellent selectivity. If you remove one or both fluorine atoms, the selectivity immediately drops off. So somehow the presence of fluorine is enabling the access to that branch product. And again, I'll explain the model in just a couple of slides. Our working hypothesis involves a mechanism by which a palladium pi-allyl species is a key intermediate for both steps. In order to probe that hypothesis, subjection of either the linear or the branched substrates to either set of conditions generates product that's either linear or branched as a function of the ligand. So we can take this substrate, generate the pi-allyl intermediate, and the ligand controls the selectivity, and that works both ways. So the ligand is controlling the selectivity. There's no memory effect, there's no template effect. We're likely going through a pi-allyl based on this experiment. Now the working hypothesis, there are three different working steps in this hypothesis, three different paths in this working hypothesis. In the first path, dissociation of the enolate from the metal and subsequent attack through an outer sphere process could undergo two different bond connections. The enolate could attack the terminal position to generate the linear product. It could attack the internal position to generate the branch product. Those would be in competition with each other, and we think that's a competition that's relevant for one of the catalyst systems. However, another CC bond forming event might involve slippage of both the enolate and the allyl group to these eta-1 coordination mode, in which the palladium templates the allylic fragment and the enolate fragment. In a pericyclic-like transition state, a palladium 2 to palladium 0 reductive elimination could presumably form the CC bond, the carbonyl, and present the allyl group in the alkene in the correct position. Now, this transition state might be dominated by the fluorine atoms that are increasing the electrophilicity of this system. So, hypothetically, our proposed model involves the attack of the pi-allyl in a nucleophilic sense to an electrophilic difluorinated position. Okay. This type of perturbation is known if you go back to classical Claisen reactions that proceed through a six-membered ring transition state. The reaction of the non-fluorinated enol ether here occurs under high temperature and good yields. The transition state would look something like this. You would have a nucleophilic enol attacking the allyl substructure to make that branch type product. The introduction of fluorine enables the reaction to occur in quantitative yield under much more mild conditions. The transition state in that case, again, in my mind, the way I think about it, you have the inductive effect of the fluorine atoms increasing the electrophilicity at this position. So it's kind of an Oompa-Loompa strategy. Instead of being nucleophilic at this position, now we're electrophilic at this position, and we encourage the attack of the allyl system. If you compare this transition state to this one here, they look very similar. We've just inserted palladium right there in between the carbon and the oxygen. So that's an analogy. It's a working model. It's a hypothesis. Maybe there's some experimental evidence and rationalization that I can provide to further substantiate that working hypothesis. So the first evidence I'll show you that helps support these two working processes. Again, in the case of one catalyst system, we have dissociation, and then these two paths that could both occur. In the other catalyst system, we have this over here. Okay. We'll use a linear free energy relationship to look at the selectivity of branched versus linear products that are formed in this reaction. Okay, so here's the series of substrates shown there, from electron-rich to deficient species. Our parent substructure with just a phenyl ring here is going to be the 0 point for this LFER. The data shown here, I don't always show the data, but since I have a little bit more time, trying to take up 2 hours, I'll throw in an extra slide here and there. I've done that along the way, and here's another one. You just don't know which ones they are. The linear free energy relationship shows an amazing correlation. Electron deficient substrates give higher selectivity for the linear product. The electron rich substrates give you product in lower selectivity. The correlation is excellent. The coefficient here of 0.45 is indicative of a cationic transition state. The comparison there also is with sigma plus. Okay, so it's evidence of a cationic intermediate. And certainly this species here is cationic, right? It's a pi allyl. There's a cation here. We rationalize the selectivity here as a buildup of a positive charge, and then the more reactive substrates that have electron deficient groups will react kinetically faster through more of like an SN2 type process. There's more of an SN1 like stabilization when you have donating groups here, and that rationalization has been supported by used by others before us. So we definitely rely on some giants in the field for this analysis. In contrast, the other process that's dominated by the 2 fluorine atoms here perturbing the reactivity, that process shows no LFER. The selectivity is excellent, it's exquisite, it's exclusive, regardless of the functional groups on this ring system. And again, we think of that as a system by which the fluorine is perturbing the reactivity, making an electrophilic center, and then the pi allyl system, which is cross-conjugated with the phenyl ring, is attacking there. So the electronic character of this R1 group really doesn't influence anywhere near as much as what's going on around this ring system in the pericyclic transition state. It's hand-waving, and it's an explanation. It's our current working model. Okay. Based on this model, we can now rationalize why the ligands provide the selectivities or give the different regioisomers. So let's walk through that rationale quickly. The bulky electron-rich ligand, if it's bulky and electron-rich, it can more easily push off an X-type ligand, in this case the enolate. The enolate requires dissociation for this outer sphere attack, so maybe it's the steric bulk and the fact that you have more stabilization from the ligand. Maybe that's the important part for this pathway. It's a bulky ligand. In contrast, a smaller electron-deficient ligand would facilitate a process for which you need the enolate to stay retained on the metal in the transition state. And so again, as you go smaller, as you go more electron-deficient, you promote this process selectively. And again, we think that it supports this working mechanism here, okay? Again, that's our working model. It might be right, it might be wrong, but we kind of left this project and moved on to other things. I'm going to cycle back and just remind you of the first sub-story I told in this sequence. It was about the benzylic substrates, and the benzylic substrates again, are activated and prepared in such a way that the activated benzylic position after decarboxylation and CC bond formation generates these products. You can see the blue bond connecting the C alpha position to the position where our electrophile was placed. While Ming Xu was optimizing this reaction, there was an annoying side product that would show up every once in a while, 3% yield, 5% yield. Wanted to get rid of it, wanted to have nothing to do with it. At one point, she ended up characterizing it and figuring out what was going on there. And it was a surprising product that was forming in small quantities. It was a product in which the enolate nucleophile had connected over to the para position. So this is a net paraselective CH functionalization, but it's from a benzylic substrate. Okay, so it's an unusual reactivity. You can see the red CC bond that's formed there. But presumably the hydrogen that was over here might have migrated over there and made the third hydrogen in the methyl group. Ultimately, that was further optimized. She learned how to selectively form that compound. There were several different systems that seemed to promote this reaction. One we never published was with an electron-rich phosphine ligand. You can see some of that data buried in the SI, but notably the presence of a base, an appropriate base, facilitated the paraselective CC bond forming reaction there. And so I'm going to show you data in just a little bit in terms of like how the base regulates the selectivity and how important the base is for the selectivity. Do note that the conditions are the exact same catalyst, same solvent, same temperature. There's nothing different other than triethylamine in those reactions. There's no other tricks going on. The reaction itself works for enough, a variety of substructures here, electron-rich and deficient. Substructures are tolerated. You can tolerate substituents at the ortho or meta position of the arene. You do not tolerate substituents at the para position. We actually need that position unblocked so we can form a new bond there. Okay. Heterocycles are tolerated. You can have electron-rich and deficient groups over here on the ketone enolate moiety. Now, there are some important properties of the base that modulate the selectivity. Note this chart is selectivity. This is not yield. This is selectivity on this axis here. We're looking at selectivity for aerylation versus benzylation. Aerylation would be high selectivity, benzylation would be down here low. So, reaction that gives 0 could still be 99% yield. It's a selectivity factor we're looking at. We're looking at that selectivity as a function of the pKa. Okay, so if you have an amine with sufficient basicity and it's reasonably small, you get high selectivity. Selection of bases here, you see trialkylamines, TMEDA, DMAP works sufficiently for this transformation. If the amine gets too big, too bulky, you lose selectivity, you selectively form the benzyl product. So you can see triethylamine relative to tripropylamine, we've lost substantial amount of selectivity. Hunig's base, terrible. Gives you all the benzyl product over here. The pK of the base is important. That's a key player. And so if you strip down DMAP into the aniline and the pyridine moieties, you can quickly see that if the amine is insufficiently basic, you lose selectivity. Those provide the benzyl product in high yield. Okay, but the pK of the amine is important. The steric hindrance of the base is important here. The concentration of the base is also important. So this data correlates the equivalence of triethylamine with the rate of the reaction. You can see an increase in rate of the reaction as we sequentially add triethylamine. The maximum is about 1 equivalent there. The rate of the reaction also correlates with the selectivity. So in this three-way correlation, the ratio of aerylation to benzylation increases sequentially up to 1 equivalent. You get really not much benefit after you go past 1 equivalent there. Okay, so the concentration of amine influences the rate and the selectivity. Amine is really controlling this reactivity. A working mechanism is shown here. I'll try to substantiate it with some experimental evidence in the next series of slides, but first let me introduce you to what we hypothesize is going on here. From a palladium-0 based catalyst system and oxidative addition would make a pi-benzyl species. The resulting carboxylate anion is a weakly coordinating anion, and so that can dissociate from the metal, decarboxylate, and then reassociate. And when it's decarboxylated, you're going to have a tighter affinity between the metal and the X-type ligand. Now, the enolate can coordinate by either the O or C base coordination modes, and computational evidence I'll show in just a little bit suggests that those are in equilibrium, 1-to-1 ratio. From the C-bound enolate, a classical CC reductive elimination would generate the benzylation product and regenerate your palladium-0. But from the O-bound enolate, perhaps the geometry between the 4 position of the pi-benzyl species and the alpha position of the enolate allow for CC bond formation between those two moieties. And through a pericyclic-like transition state, a reductive elimination that takes your palladium-2 down to palladium-0 and generates a CC bond would also present an acidic methine proton. It's acidic because you have two allyl groups attached to it. You also have a fluoroalkyl group. You expect each one of those to sequentially acidify that position. With an acidic position, a basic amine might deprotonate this position, allow aromatization, and transfer the proton over there to the benzylic position in an inner sphere process. So that's the role of the amine additive in this working model. You deprotonate, you reprotonate, you generate the aerylation product, and then you regenerate palladium 0. That's the working model. I'll show you an array of experimental data that supports this and or refutes some other models. Initially, I'm going to demonstrate data suggesting that you have free association here, solvent separation of the carboxylate anion from the palladium. So a straightforward experiment here would be a classical crossover experiment. You have a labeled substrate, you have the methyl and isopropyl, and then H and methoxy. If you have crossover, you would expect a 1-to-1 to 1-to-1 to 1 ratio of 4 products, and with experimental error, we get that. Okay? 15, 15, 15, 13. That's statistically what you would expect within error of the measurement. So we get crossover. We think it's early stage crossover. Another classical experiment, if you aim to probe for metal hydride or metal aryl intermediates, is to run the reaction in the presence of a deuterated solvent. If you have a discrete metal hydride or metal aryl intermediate, you would see introduction of the deuterium onto the aromatic ring. The reactions, when run in methanol, do not produce any deuteration of the aryl ring. The reactions form the anticipated product in addition to some material that's deuterated at the alpha position. And so that's evidence of an enolate that can dissociate from the palladium, or is dissociated after the decarboxylation, okay? So we deuterate this position, we have anionic character there. We don't seem to have palladium metal or palladium hydride or palladium aryl intermediates. Discrete evidence for the transfer of the proton from the para position to the benzyl position was established using a simple deuterium labeling experiment. You can see the transfer of the deuterium over to the benzylic position is excellent. Now the transfer of the deuterium occurs after the rate-limiting C-C bond forming event. Okay, you make the C-C bond, and then the deuterium transfer happens. In order to probe that, we had to invent a new type of substrate, a tri-labeled substrate. I haven't seen this type of experiment before. In this substrate, we have a label here on the ketone moiety, a label there on the benzylic moiety, but we also have a third label over here on the benzyl moiety. 3 labels, 2 by 2 by 2, possibly 8 different products if we have full scrambling of everything, but we're only going to see 4 products in this reaction. This reaction specifically probes whether transfer of the deuterium happens after C-C bond formation. If transfer of deuterium happens with an inner sphere process after C-C bond formation, the deuterium will stay attached to all the products that contain isopropyl. If it's an inner sphere process, the deuterium should not cross over to the other substrate. So that's what we're trying to probe here. In fact, that's true. I'm walking through it because, yeah, it's going to be true, right? Okay, so we see 4 products. The 4 products have the labels as shown. Most importantly, I bolded, the deuterium stays attached to the moiety bearing the isopropyl group. In all of the products we see, the hydrogen stays attached to the methyl. So the deprotonation, reprotonation occurs within the solvent sphere at the end after you have scrambling, after the C-C bond formation. Evidence, computational evidence, was further substantiated by Paul Chung's group, great collaborators. Initially, I'll rule out any suggestion that there's a thermodynamic process controlling the selectivity. Computationally, the aerylation and the benzylation products are equoenergetic. There's no thermodynamic control in this system. I already suggested that the C-bound and O-bound enolates are equi-energetic, and within computational error, you can see that's true. So those should be existing in free equilibrium, back, forth. The CC reductive elimination to make the benzyl product involves a transition state. That's 27.7 kcal per mole in energy there. That transition state involves dissociation of a phosphine ligand to make a less stabilized palladium intermediate, then slippage of the pi-benzyl moiety to an eta-2 coordination mode is required for forming the CC bond there. That's a unique transition state. We weren't expecting that. But ultimately, that generates the benzylation product. Now, when thinking about the mechanism, that pericyclic rearrangement type process to generate the aerylation product, let's look at the energy trajectory for that. So the transition state for that pericyclic intermediate is lower in energy, 23.5 kcal per mole. That's actually lower than the transition state over here. And the intermediate that's de-aromatized but still coordinated to the palladium is actually pretty reasonably placed. 11.5 kcal per mole there. So in these reactions that are forming benzylic products, these computations suggest that you have an equilibrium here, you have a lower energy pathway actually going over here, but with no opportunity to do anything. Microscopic reversibility, you do the retro 3-3, you come back through this energy landscape, go back to the enolates. Ultimately, you're going to keep going back and forth until you get to the benzylation product. That's what these calculations are showing. Okay. Now, in the presence of an escape route, perhaps we can trap out this intermediate. That escape route is enabled by the amine base. I already showed you how important that amine base is for controlling the selectivity. So here's our activated methine, deprotonation of the activated methine by trimethylamine. This is a model for triethylamine. So in the model system, the deprotonation has an energy, a transition state energy of 26.5 kcal per mole. That's lower than the transition state over here for benzylation. So you have the right amine, a small amine, a sufficiently basic amine, the energy associated with deprotonation here, and presumably the subsequent step of reprotonation of the benzylic position there's a low energy pathway there. You form the aerylation product. If the amine is insufficiently basic, the computed energy level is too high. So pyridine doesn't work. Pyridine doesn't give you this product, and the computations support that. Here we're at 32 kcal per mole, certainly higher than your 20.7.7 over there. Okay, so these suggest the work. These support the working model. It is the model that we're going with right now. Reviewers weren't happy enough. They thought it was a fluorine trick. They said if you can only make fluorinated ketones, that's not enough. That's not impactful enough. So in response, I'll show you a couple of examples here in which we can flip the selectivity of other reactions that are non-fluorinated using the same trick. The trick is an amine trick. This is a reaction from a former colleague, John Tungy. His office is right around the corner from mine. He had this nice publication shortly after I joined KU. It was a palladium catalyzed coupling reaction. Again, oxidative addition, decarboxylation, and you couple the alpha position of a nitrile to the benzylic position. Really nice reaction occurs in over 90% yield. Taking his same reaction conditions and presenting those conditions with a base flipped the selectivity. So instead of a CC bond forming reaction at the benzylic position, now you get a paraselective CH bond formation just with the amine base. The selectivity isn't perfect. You can further optimize the condition, change the catalyst system, change the amine, and we get excellent selectivity, synthetically useful yields of the paraselective product. The amine base, in this case, the T-butyl TMG, is really driving the selectivity here. And a mechanistic analysis, if you do that, you'll perhaps draw something like this. You still have your pi-benzyl coordinated to the nitrogen of the nitrile. The nitrogen can then form a bond from the alpha position to the C4 position. A pericyclic-like transition state in the reductive elimination process would generate an activated methine proton. Again, deprotonation, reprotonation over here would aromatize the system. Okay, you need a little bit of a stronger base there to get this one to go because you don't have the fluorinated groups further acidifying this position. Nonetheless, we're still controlling selectivity with the base. Okay, so what's next? Maybe we can exploit this strategy to take on other challenges, and one challenge might be CH functionalization of feedstock chemicals. Certainly we like to take oil reformats and make value-added compounds using simple systems, direct systems. Let me show you one thought on how you might take toluene and do a para-selective functionalization of that molecule. It's a challenging reaction because the weakest CH bond is actually going to be the benzoylic position, so that's going to be easy to functionalize, but how would you functionalize this over here? An additional challenge is the regioselectivity, so if you try to functionalize the para position over the meta or ortho positions, the statistics are against you, right? You have 4 other positions, we want to do this one position. We want to get this position, we don't want to touch the other CH bonds. So you have regiochemistry issues, you have chemoselectivity issues. Let me suggest one opportunity to do this transformation, one process that might be used to selectively functionalize the para position of toluene. Specifically, the strategy will involve functionalization of the weak CH bond and then transfer that functionality over to the para position. So in an early synthetic sequence, a radical classical bromination of toluene generates benzyl bromide. We get rid of excess HBr just by bubbling through N2. We do send that gas through traps. Don't just push HBr out into the atmosphere, push it through hydroxide traps properly. From there, in the same pot, you throw in the pronucleophile, platinum-based catalyst system, a combination of bases, and you get the para-substituted product in a single yield from toluene. Now that product itself might not look the most interesting, might not be the most useful, but perhaps with some synthetic creativity, some further functionalization, halogenation, classical just SN2 heterocycle alkylation chemistry, you might make compounds of increasing complexity and some of which are at the complexity of FDA-approved therapeutics. So there's lots of things you can do. You can functionalize the nitrile, you can functionalize over here. Perhaps your pronucleophile has different moieties over here, different groups there. Perhaps we can get to other interesting substructures with this type of strategy from toluene. So, that there is basically where I am ending the day. I've taken you through quite a few different transformations. Hopefully you've seen the evolution of a project and a proposal into a program. So some of you individuals who are thinking about being a faculty member someday, many of us get really focused on projects, but if you get that first reaction to work, the second reaction to work, how do you see 10 reactions, or how do you see a career develop, even after you get that first one? So be thinking about that also. What's the difference between a project that a student might be working on in a program? Okay. Hopefully, there's been some learnings on the synthetic part that complements some of the things we've been talking about on the med chem side. Hopefully the appreciation of the physical organic chemistry and the physical chemical perturbations imparted by fluorine was apparent here. I hope also it was apparent on the other part of the course. And if it wasn't, I really haven't done my job. So other than that, I'm very appreciative of group members. I've highlighted individual ones throughout the slides who contributed to the projects that I demonstrated, the project that I showed. The work here had been supported by a series of young faculty grants that ultimately, were, and also larger grants from the NIH. So grateful for all the funding we've had, but the ones that supported the project shown here are highlighted there. Other than that, it's been a fun week, a week in which I'm losing my voice right in front of you guys, so I'm going to be quiet there. Thank you all, and it's been a fun interaction, and I hope that this inspires you to do great things in your futures. All right, so thank you.
So I think we can take a couple of questions. Any questions? So I
phenyl is,
With its alkylating ketones.
yeah. So phenyl is on a geminal position. If that phenyl is in vicinal position, what kind of like reactivity will have?
So it was this reaction here that you're asking about?
Yes.
And specifically, you're asking if I have a phenyl group where?
Vicinal position.
Sorry?
Vicinal position.
Vicinal. So if it's over here?
Yeah.
So those substrates did not work well. I'm going to maybe go back a couple of slides here and see if I can find it. So you're saying if I had this and I had a substrate here with a phenyl group here? So I have two different comments there. If you want, I think that's this substrate down here.
That phenyl is in next position of that part.
You want it here?
Here, sir.
Yeah, we didn't explore that one. I don't know mechanistically in my working, the model in my head and that I showed you. I think it should work okay for either system. Note that that's if you do not have this one and you just have the phenyl ring there, then you don't have the issue of linear branched. So either make a CC bond on either side is chemically equivalent. Okay, I think it would work, but I don't have experimental data to support that. The pericyclic transformation would similarly work just fine in the working model.
And that is only one product is formed. Instead, if you use any kind of ligand.
If I use any kind of what?
Ligand,
Yeah, sure. And it's definitely true in cross-coupling chemistry in general. Sometimes you make like subtle changes to your substrate and then you just need a different ligand. That's why there are so many phos ligands out there, right? Is just minor changes to the substrates require modification there. Okay.
In the last stage, you have done the nature chemistry paper.
You have to talk a little bit louder because that's kind of loud too. So in the Nature Chem paper, what?
So in the last mechanistic study, you have done the
Yeah. Which mechanistic part of this, or which study?
nature chemistry paper.
This is that one.
last time we
Go back to the side.
You want the computational part?
Cyano, that is dimethyl cyano.
So communication. Sorry, I thought it was saying Nature Chem.
Dimethyl cyano instead of dichlorophosphate, you have
the last one.
The last work?
Last
What do you want to see though? Like the mechanism? So I guess what's the question? This is the mechanism. So what's the question?
So the same, what's your question?
Yes, all the reaction was done with dichlorophosphate and the last, as you told, like we were suggesting fluorination. So you have not defined scientific performance.
Right. So what about the question?
If the same cyano we have and dichlorophosphate.
Oh, dichlorocyano. Okay.
Yeah, so the question, did you do it with difluorocyano? No, we were struggling to prepare that substrate. There are other challenges that you should be aware of and thoughtful when you're preparing substrates. So one substrate that we had worked with a little bit was a substrate for which if you replace one of those methyl groups with a fluoro, you make the fluoromethyl product. It turns out when you subject that to base, you competitively eliminate. So if you have a fluoro here, then you have a vicinal hydrogen and you can eliminate and make an alkene. So you can get some of the product, but you also get some elimination. And we can't completely solve it, just like optimization. I think process groups with high throughput experimentation, Bayesian optimization strategies, I think you can solve that now. But at the time, it was really tough and tricky. You get 20 or 30% yield of some of these other derivatives, but again, just never really solved it well enough.
And sir, one more question. The first slide where you have shown that crystal group, if we remove crystal group with the activated crystal like N-hydrox, N-ketimine, trifluorilation,
I think I know which one. Yeah, where you're making the new reagent. So that would be back up here in this section.
Yes.
Yep. So what about it?
You know what Medicinal told that remove the like leaving some byproduct was coming like methanol
Mhm.
decreases. So instead of that, if we have activated with like an element.
Sure.
So,
So, right. So, I think that would look something like that with an NO on it. This is a subset of things. We probably tried 3 times this many. I don't know for sure that we tried the N-hydroxythalamide, but I speculate that we did try it. This is just kind of what fit on the slide and what I use for presentation purposes. The SI has some more examples. So, okay. Certainly there are other things that can do transesterification reactions. Perhaps there are other solutions for this problem.
Okay, I think so. With no more questions, now I think we will take a break because we need to quickly come back for the lecture section for this GIAN course. So we'll just thank Dr. Arkin again. Like quick 10 minutes break. We have tea, and after tea, those who register for the GIAN course should again gather back for the director function. We have also Markham here. I have connected Professor him and he agreed to face this function. So we will join back like a 10 minutes. Go there and try to sit on a phone. Put some paper like no, not like that. Take back outside.
Good evening, everyone. It gives us immense pleasure to speak on this valedictory occasion of the GIAN course on understanding the mystery of fluorination in medicinal chemistry. Over the past 5 days, from 3rd to 7th, we have the privilege of exploring a wide range of fascinating lectures that deepened our understanding of the power of fluorine chemistry in drug discovery and design.
I would like to call Professor Altman, Professor Bharatam, and Dr. Deepak Salunke to please ascend the dais. So please. Now I'd like to request Dr. Deepak Salunke to summarize in the GIAN course. So please.
Okay, so I think I'm just thinking that it's just, I don't know, last 5-6 days, it went on like so quickly. Initially I was so much tensed, not very well prepared, but I think our speaker was all excellent, and he just like turned the things like so easy, like for all of us, because once the course started, it was like all wow, every day was so good. So just because I wanted to, because we are on camera, so I just wanted to summarize what all thing happened. Professor Bharatam was involved in the course, but still a few parts I just would like to summarize. So so we had many lectures. Professor Altman. So we started on day 1, that is Monday, November 03. Professor Altman started with these lectures on physical principles, stability, reactivity patterns of fluorine and fluorinated groups. Then in the second day, he talked about controlling molecular conformations using fluorine and fluorinated substituents. Third day, it was about exploiting fluorine and fluorinated substituents to modulate pKa, solubility, log P, distribution, and influence ion pair interactions. And you all notice that with the very interesting examples, like how he has shown, like how conformations, these pKa values can be altered by substituting like fluorine at different positions, fluorine or a CF3. In the next subsequent day, that is day 4, he talked about exploiting fluorine and fluorinated substituents to modulate metabolic, hydrolytic, and thermal stability. So again, as a chemist, now it is a very interesting that we can turn a chemist to a thinking chemist and then plan our molecules. So that was very interesting. On day 5, he talked about ligand-protein interactions enabled by fluorinated compounds. All these lectures, the morning sessions, apart from the lecture, we also have seen that the tutorials, which were so interesting with very prominent examples, and then how he took all of us through these tutorials in a very personal manner, clearing all the doubts, and then it was very much like a one-to-one interaction. So apart from this, we also got a chance Indian faculties to to pitch in little bit and try to contribute to this course. So afternoon sessions, we listen to different structural diversity of pharmaceutically active fluorinated organic molecules. Then we also seen a few strategies to introduce fluorine in organic compounds, and we have seen an array of reagents for fluorination chemistry. Then next day we saw several metal catalyzed fluorination reactions. We have also seen pharmacoinformatics on the importance of fluorinated organic molecules in drug action and studies. I'm thankful to Dr. Ravi and Dr. Professor Bharatam for helping out in these. Then we had also very interesting lectures on how light mediated CF bond activation can be used as a tool to again design difluorinated compounds. So that was very interesting. On the same day, we also listened to several electrochemical toolbox for fluorination chemistry. Specifically, like how from GEM difluorocyclopropanes we can synthesize trifluoromethylated aziridines. It was again an interesting talk from speakers from IIT Ropar, Professor Banerjee and Professor Chatterjee. Then we have also like experienced like how to characterize fluorinated compounds, looked into several aspects of fluoride-19 NMR. We have seen how it is different in 1H, how it influences 13C, how we can utilize like 19F NMR and then do several decoupled experiments to understand what is going on and where is the position of fluorine in the molecules. Also, there was a interesting discussion about additional experiments, 1D as well as 2D experiments to see how we can actually characterize these molecules. Apart from that, we have also seen some metal catalyzed metal free strategies to introduce or to make organic compounds with fluorine, and then like Dr. Ramashastri showed that how to how he characterized his compounds by using fluoride-19 NMR. Later, we have also seen a little discussion about fluorinated compounds and their importance in material chemistry, from the material chemistry aspect. And then today evening after lunch, we all have experienced such a fantastic lecture from Professor Altman. So I think this all thing was very much possible only because of like time Professor Altman shared with us. So with this, I will ask the next proceedings. Yeah, thank you.
We would now request to Professor Bharatam to kindly share a few words about the course. So please.
Well, it's, you know better than me. I attended only a few sessions. Most of you attended all the sessions. So I don't have to summarize the whole thing, but I would like to put my perspective. Professor Salunke used one word, thinking chemist. I like that word, phrase. The idea was that you will come across in future many varieties of chemists. They simply know how to do one reaction or two reactions, and then whole life they spend with it. But there are a few others who don't know much. They only know stand in front of the column, put something on the bottom, collect something on the bottom. They don't know what, they don't think at all. They simply stand and watch their WhatsApp messages and spend their whole life. 5 years are over, PhD degree granted. There are such chemists. There are many others who know exactly what kind of NMR peak they are expecting, which peak is missing, which is coming as a function of the reaction, which kind of reagent to be added, which kind of solvent to be taken, and they are really doing varieties of good things. Over and above that, there is a requirement to incorporate physical perspective to organic chemistry. That's what we have seen in the last 5 days. Every example that's given by Professor Altman included not only the organic chemistry principle, but also the physical chemistry perspective, and to understand the conformational preferences, energy requirements, then the steric effects versus the electric effects, and then the pharmacophoric features, as well as hydrophobic perspective versus the hydrophilic perspective, and many other aspects. So, as a result, we have covered lots of modern organic chemistry in this series of lectures. So I want to thank Dr. Salunke also for taking this initiative and starting this and taking interest in this kind of GIAN courses. For example, I will have to confess now, once last time when you came here, immediately I got highly motivated, and I started filling a GIAN course proposal. After doing work for 3-4 days, I gave up. I know it's not a very easy task. Conducting a GIAN course and identifying an appropriate professor and attracting his attention to the benefit of our students is not a small achievement. So I appreciate you for that, and you have done more than 2 or 3 in this area. 8. Yeah, so it's a special skill that is required. I could not manage that. So I realize the importance of your homework on this front. And of course, we all thank Professor Altman for taking us through the journey of physical organic chemistry versus organic chemistry versus pharmaceutical chemistry and all aspects of chemistry with reference to the fluorine specialized compounds. Thank you.
Now, I would like to request Professor Altman to share his overall experience throughout this course.
So hi again, everybody. Welcome back. I can shut this now. I'm going to sleep tonight. So, Deepak, we've known each other for some years. He's also, actually, Deepak's really instrumental, a builder. He's an individual who has reached out to me at various points to support his junior colleagues. And so this interaction that's been over a decade now also involved him supporting one of his former juniors to have a postdoc in my lab. One of the individuals you saw in the last, like the very last experiments, Mani Kandan, Mani, was his junior back in Taiwan when you were a postdoc. Mani was a grad student, so he certainly is an individual who looks out for people, his juniors, and I'm sure he does the same with his trainees as well as trainees that are at NIPER in general. So it's a long-standing interaction, and thank you. It's good to continue it. Thank you to other colleagues and faculty who participated and took their time to come share their science with us. It was very nice. Thank you to the GIAN course. We all need to thank the organizers of GIAN overall and the funding agencies that support the education of individuals. That's certainly important. The investment in the young scientists pays off decades down the road, so it's foresight, it's forethinking to continue to support science as you think about the next decades of scientists. Hopefully there's some fantastic ones here in the room. In terms of the material, hopefully you experience the passion, the enthusiasm that you can have for a subject. For me, this area started as just a simple inquiry, a questioning, an interest in understanding things I didn't understand, and some of it was in the literature, but that was also 2005 and 6, and most of the things we talked about came after that. Most of the citations and references were after the time when I was just a graduate student. And so continuing to follow up with the literature is certainly something that everybody should be doing. It's more difficult as you move forward in your career to go back and keep up to date with the journals and the newest developments. Nonetheless, something I challenge you to do now as a trainee, but also moving forward. Hopefully, as you continue to move forward, you grow as a scientist, and the lessons and the principles that we discussed here might be applied to your future projects, your future programs in industry and academics, wherever you end up in your career. Do make sure that while we talked about fluorine chemistry, many of the principles do not require fluorine to be in the molecule. Many of the principles we discussed can apply to many other types of functional groups, and just a deep thought in the physical basis for the perturbations and molecular reactivity, or how that molecule believes small molecule interacts with the biological system, is certainly something to keep in mind. The basic principles you can apply anywhere. the basic principles will be important for your discovery campaigns in the future. So with that, I just wish everybody the best of luck in your graduate careers, finishing up, whether you're at the beginning of your career or the end of the career. Good luck getting the next position. Good luck to you, long term in your career. So thank you all.
We would now like to request the participants to come in front as their names are called to kindly receive their certificates. We'll start from.
Yeah, maybe some members want to say.
Sure,
Yeah.
Sure, ma'am. Okay.
So, hello everyone. First, I would like to thank Deepak sir for bringing up this brilliant opportunity to NIPER Mohali. And then I would like to thank Professor Altman for these insightful and interesting sessions. The learning through these 5 days course was truly transformative, sir. The way you explained all the basics, all those concepts rekindle my confidence, and the way you linked everything with the physical organic chemistry and all those beautiful ESPs trained me to approach chemistry more deeply and creatively. Couple of months back, I was just writing a line about fluorine in my manuscript, so I just read somewhere that fluorine is just a small atom with a big ego. So now I would like to appreciate that how it can actually perturb all the electronic properties positively and powerfully and meaningfully. So I could go back and at least look in a drug that what fluorine is possibly doing, or I could insert them in the drugs which I design in future. Thank you, sir.
Anyone?
Maybe first year student, first year master's student.
They're always sitting on the last row.
Okay.
So we. Okay. So we now like to request to the participants to come forward as their names are called. We'd start from Syed Minazul.
Tarun Kushwa.
So 5 names will be called so that we can say on time.
Yeah.
So all 5 come together and we take a photo.
I take this opportunity to tell you, all chemists should be careful about their safety. And that's why I'm coming with a quote. In all your photographs, I will be with this quote so that you can remember the safety aspect of chemical exploration.
Rizwan Ahmed, Saurabh Negi, and Keith Neil D'Souza. Dr. Ritu, Mr. Rakesh, Ms. Kajal, Mr. Satyan Gautam, Mr. Abhishek Adhikari.
You are in front of camera.
I will take one from his hand and then we take a group photo. Okay? Take one. Like everybody takes a certificate with his hand and then we stand here for a group photo. Come. Yeah, take a photo first.
Nobody has a camera.
No, actually there is a video going on, so
Mr. Arup Rai, Mr. Danish Sharma, Mr. Harkar Pankaj Sanjeev Rao, Ms. Kriti Mehta, and Ms. Anshu Prajapati. Ms. Rishika Suresh, Mr. Rahul Kapse, Dr. Sumit Sood, Mr. Soumik Ghosh, Mr. Sujoy Saha, Ms. Aditi, Ms. Anjali Dhaval, Ms. Pratibha Sharma, Ms. Arzu Kamboj, Mr. Satyanarayan Mohapatra, Dr. Rahul Kumar, and Ms. Binita Sehag. Ms. Rajni, Dr. Ashish, Dr. Prince, Mr. Sagar Kumar Rai, Mr. Saudipta Kansari, Mr. Sanjeev Kumar, okay, okay, sure.
Those, there are few, I think, who are not announced. Maybe they can come at the last. Okay, few names are not announced because the attendance was not 100%. But I think those who are there, like I think आप लोग हो ना, जिनका जिनका नहीं हुआ है उनको सर्टिफिकेट बस उनको कोई नहीं हाथ में दे दो। प्लीज जिनका जिनका नहीं हुआ है आ जाओ।
would now like to request Dr. Deepak Salunke to present a vote of thanks.
Yeah, thank you. Again, I'm back. Okay, so I am really happy here to present this vote of thanks. I am very much thankful to first, like the most important person, Professor Altman. And I'm really thankful to him. Professor Bhartam mentioned that like he wanted to apply and then he just gave up. And I think that is the only reason is that the response from the foreign faculty, because I feel lucky that I could find a person who was, because he mentioned that the person, you need to find a person who is actually willing to pass on knowledge and then like he's traveling, spending so much of time for the good of students. So whenever in this last 5 days, 6 days, 7 days I think, because he was here 2 days before, and whenever I asked, like, sir, please, can you give this lecture? Can you please, like, instead of 1 hour lecture, 2 hour lecture, maybe like, why not to give, because we have only half an hour, why don't you give a half an hour lecture at ISER, INST? And he said, okay, whatever, if there is something good for students, I want to do it. So that is a kind of a dedication, I think, because he was here, he like, we, I think, didn't spend any time also to like see places and all. He was like always on top of his work, always ready to give lectures. Day one he arrived, immediately next day he was like, he sent me the material to be shared with all of us. And then even when there is a break time or something, he always want to be perfect for his lectures, and he wanted to, and you have seen his time planning, like when we told that okay, we have a break in 30 minutes, right, in like 30 points, maybe 05 or 29.5 minutes his lecture will be over. Such a nice planning. I think there were so many things to learn, and I really feel that because you were so near to us, I think that inductive effect should actually influence a great teacher, great researcher within us, and I'm really thankful to Professor Altman for this. I should thank MHRD, or now it is Ministry of Education, who have initiated this global initiative of academic network, a very interesting program, because this started in like about a decade back. And at Punjab University, I was like, I thought, okay, why not? Because I started teaching, I came from industry, postdoc. I thought, why, this is a very good initiative. If you want to improve the teaching skills, why not to see if there is a, like, why not to bring people who can be, who are very good teachers, and then definitely while working with him, it was such a learning experience. Even reading his emails, reading his material he's sharing, it was a very immense learning experience for me. And I hope students also, my students, they are also getting like help, because they get to be with Professor Altman or any foreign faculty longer time. I'm thankful to Professor B.S. Murthy, who is the director IIT Hyderabad and a national coordinator of this GIAN, for all this process. In fact, I want to mention that during the review, our proposal was reviewed, and there were comments like it was not rejected, it was accepted, but there was a comment that the Indian faculty was having not much experience in fluorine chemistry. It was the right comment, but then we replied that yes, we will involve a few faculty from India, the experts from with nearby institutes, to talk about this, and then I think it worked really well. I think you might have experienced that. I'm thankful to Professor Gurjasprit Singh, who is the local coordinator of GIAN. In fact, such a wonderful, very helpful person. And whatever demands I had, like I want to see if we can arrange this course here, he was like, okay, let's see, we can work it out. He talked to Professor Renu Vig, Vice Chancellor Punjab University. She was like wanted to, because she's at a university, she wanted this course for Punjab University students. Somehow then I had to talk to Professor Panda, Director Naipur Mohali, and he called her and then requested that this all arrangements have been done at Naipur, and this course is all open to Punjab University students. He welcomed all the students to Naipur campus. And then finally it worked out. So I'm really thankful to both of them for their support in arranging this course over here.
I'm thankful to my students who really are like behind my students at Naipur Mohali. So they actually helped me a lot in this course. My students at Punjab University, they are behind the scene always, but then this time it was all the show mostly helped by my students at Naipur Mohali. And you have seen the master students, first year students, they have really like nicely arranged everything, tea, coffee, like all everything, like they planned it nicely. Also I have told them that to be make sure that you don't miss classes. Okay, so it was all like planned well. I hope you are happy with the whatever we planned. I'm thankful to the staff from Naipur who actually helped to make all these arrangements. Without that support, it was a little difficult. And I'm at the last, I would like to thank Dr. Madhuri, my wife, actually, with whom we three actually, we both had a little interaction with Professor Altman earlier at Kansas. So I thought maybe then we both were involved in writing this course, and she was a co-coordinator in this course. So I think, last but not the least, I am thankful to Professor Rahul Jain, the head of the department, Medicinal Chemistry, who actually supported me to arrange. When I went to him that I want to arrange it here, he said, yes, go ahead, because that your institutional support is very important. I'm very much thankful to Professor Tikku, Dean, and Professor I.P. Singh, who inaugurated this course. So without their constant support behind me, it was not possible for me to arrange this course. And all my friends, actually faculty from nearby institutes who came with my invitation, spent time with all of us, and delivered very interesting talks. So I'm thankful to all of them. So, and I'm thankful to the participants who actually looked into the course, thought that it could be useful for them, and they registered for the course and spent time last 5 days and learned something out from there. So with this all happy note, I take so I'm thankful to all. I'm thankful to our friend. I forgot, what is your name? Darshan. Yeah. So he is listening to all chemistry without any chemistry background, and I'm really happy to see his patience. So you know at any kind of work you need a patience. So you see, he was without any disturbance to the all class. He was patiently making sure that everything, his job is done the best. So with this, I would like to now close this, and thank you.